Hello there, and welcome to Science for Sleep, the place where curiosity slows down, explanations take their time, and the universe feels just a little quieter than it does during the day. Tonight, we're going to spend some time together exploring something truly enormous, something so large that even the word enormous hardly feels adequate. We're going to talk about a star that astronomers sometimes describe as a kind of cosmic behemoth, a star so vast that if it were placed where our sun sits now, it would swallow the orbits of planets you already know by heart. But there's no need to rush ahead. We'll get there gently. Before we begin, I'd like to ask you something simple. Where are you listening from tonight? Are you under a blanket in a quiet room, perhaps with a dim light somewhere nearby? And what time is it where you are right now? Late evening, early morning, or somewhere in between? It's always a little comforting to think that while we listen to the same story, each of us is sitting in a slightly different moment, a slightly different place on Earth, all connected by the same quiet voice and the same shared curiosity. If you find this kind of slow, gentle exploration soothing, if it helps you relax or drift, then feel free to like the video or subscribe. It helps this calm little corner of science reach more people who might need a peaceful ending to their day, and if you're already settled in, comfortable and ready to listen, then we can ease into tonight's journey together. Because tonight we're going to think about size, not the kind of size we deal with in daily life, like the size of a house or a mountain or even a continent. Those are large by human standards, certainly, but in the universe they are very small things. Tonight we're going to talk about the largest stars ever discovered, and in particular, about one that some astronomers have informally nicknamed Behemoth, a name that feels fitting, not because it is official, but because it captures the sense of scale we're about to explore. Now, when most of us picture a star, we imagine something like the Sun, a bright, steady sphere of light and heat, large enough to dwarf Earth, yet still manageable in our minds. We can picture the Sun hanging in the sky. We can imagine its warmth on our skin, and we can grasp, at least roughly, how big it must be compared to our planet. But the Sun, enormous as it is not a particularly large star. In fact, in the grand catalogue of the cosmos, it's considered fairly ordinary, even a bit on the smaller side compared to the true giants. There are stars out there so vast that if you tried to fly a spacecraft around them at the speed of a jet airplane, circling their surface once would take months, perhaps years. Some are so large that light itself, travelling at 300,000 kilometers per second, needs hours to cross from one side to the other. Just pause for a moment and let that settle in. Light, the fastest thing in the universe, taking hours just to cross a single star. It begins to change the way you think about size. What makes this even more interesting is that the biggest stars are not always the most massive. That might sound surprising at first, but in astronomy, size can mean different things. A star can be huge in diameter but relatively light in mass because its outer layers are spread thinly over an enormous volume. Other stars are smaller in size but far denser and heavier. So when astronomers talk about the largest star, they usually mean the one with the greatest radius, the one that stretches the farthest from its centre to its outer atmosphere. And that's where things start to get truly astonishing. Because some of these stars are so large that if one replaced our Sun, its surface would extend beyond the orbit of Mars or Jupiter or even Saturn in extreme cases. Imagine looking up at the sky and seeing not the distant Sun, but the glowing surface of a star filling half the heavens, its edges stretching far beyond anything the human mind evolved to picture. Of course, no such star sits in our solar system, and that's probably for the best. But far out in the galaxy, these giants do exist. Astronomers have found them, measured them, argued about them, and occasionally revised their estimates as better data arrives. And that's part of what makes this story interesting. The title of largest star is not fixed forever. It changes as our observations improve, as new stars are discovered, and as older measurements are refined. So the idea of a cosmic behemoth is not just about one star, it's about a whole category of objects that push the limits of what a star can be. To understand how such giants exist at all, it helps to begin with something familiar. Think about how stars are born. Every star begins as a cloud of gas and dust, floating in space, cold and quiet. Over time, gravity pulls that material together. The cloud contracts, grows denser, and eventually forms a hot, glowing core where nuclear fusion ignites. That process, hydrogen atoms fusing into helium, releases energy, and a star is born. Most stars end up modest in size, like our Sun or smaller, but occasionally conditions allow a truly massive amount of material to gather. When that happens, the resulting star can become a giant, or even something larger still. Yet here's the curious part. The biggest stars we see today were not always so enormous in diameter. Many of them began their lives as hot, bright stars only a few dozen times larger than the Sun. Over time, as they aged, their outer layers expanded, swelling outward until the star became hundreds or even more than 1,000 times the Sun's size. It's a bit like watching a glowing ember slowly puff into a vast diffuse cloud, still hot, still luminous, but spread over a much larger space, and as a star expands, its surface cools. That's why many of the larger stars appear red or orange rather than white or blue. Their immense size means their outer layers are cooler, even though their cores remain unimaginably hot. These are the red supergiants and hypergiants, the true giants of the stellar world. Some of their names might sound familiar if you've ever looked into astronomy before. Stars like Betelgeuse, Antares, or UY Scuti have captured attention for years because of their incredible scale. But even among these giants, there are candidates that stretch the limits further still. Stars whose size estimates are so extreme that astronomers approach them with a mixture of excitement and caution. And that's where the idea of Behemoth enters the story. Now, it's worth pausing here to notice something about how we react to numbers in astronomy. When you hear that a star is 1 billion kilometers wide, or 1,000 times larger than the Sun, those numbers are so far outside everyday experience that they can begin to lose meaning. They become abstract, distant, almost unreal. So instead of thinking only in numbers, it helps to use comparisons. Imagine the Sun as a sphere about the size of a large beach ball. Earth would be a small peppercorn orbiting several meters away. Jupiter might be a grape somewhere farther out. Now imagine replacing that beach ball with something the size of a large house, or a stadium, or a mountain. At some point, the scale becomes difficult to picture not because it is complicated, but because nothing in our daily lives prepares us for it. And yet, the universe is full of such extremes. There's something quietly humbling about that. Not in a dramatic or overwhelming way, but in a gentle, grounding sense. The universe is vast and we are small, but we are also capable of understanding it, little by little, piece by piece, simply by listening, thinking, and imagining. Another interesting aspect of giant stars is that they are rare, very rare. Most stars in the galaxy are small, faint red dwarfs, far smaller than the Sun. Giant stars are the exception, not the rule. They burn their fuel quickly, live short lives, and end in dramatic ways. In a sense, they are the fireworks of the cosmos, brief, brilliant, and spectacular. That also means that when astronomers find one of these giants, it becomes an object of intense study. Telescopes observe them in visible light, infrared, and other wavelengths. Scientists measure their brightness, their temperature, their distance, and from those pieces of information they estimate size. But estimating the size of a star hundreds or thousands of light years away is not easy. In fact, it's one of the more challenging tasks in astronomy. The stars are so distant that even the largest telescopes often cannot resolve their surfaces clearly. Instead, astronomers rely on indirect methods, combining different measurements to infer how large the star must be. And sometimes, those estimates change. A star once thought to be the largest known may later be revised downward, or another star may take its place. So when we ask, is this the largest star in the universe? The answer is often, as far as we know, for now. Science is comfortable with that kind of answer. It leaves room for discovery. Right now, as you listen, there are stars out there larger than anything the human mind naturally pictures, glowing steadily in the dark, light travelling across immense distances, crossing the silent spaces between galaxies, eventually reaching telescopes, cameras, and finally stories like this one. It's a long journey for a beam of light, sometimes thousands of years, sometimes millions. And yet here it is, reaching us, giving us a glimpse of these distant giants. In a way, learning about stars is like listening to echoes. We are hearing stories that began long before any of us were born, stories written in light, still arriving, still unfolding. When people first hear about the largest star in the universe, it sounds like a straightforward idea. Bigger is bigger after all. We measure the size of things every day. A larger house has more rooms, a larger mountain rises higher, a larger animal weighs more. It feels natural to assume that stars follow the same simple logic, that the biggest star is just the one that contains the most material, or looks the largest in the sky. Yet once astronomers began studying stars carefully, they discovered that the word largest is far less simple than it sounds. In fact, depending on what you measure, different stars can claim the title in different ways. To understand why, it helps to slow down and look at what a star actually is. A star is not a solid object like a rock or a planet. It doesn't have a sharp surface you could land on, or a clear boundary where the star ends and space begins. Instead, a star is a vast sphere of hot gas, mostly hydrogen and helium, held together by gravity and powered by nuclear fusion in its core. The outer layers of that gas gradually thin out as you move farther from the centre, fading into space rather than stopping abruptly. So when astronomers talk about the size of a star, they are already making a choice. They must decide where to draw the line, where to say this is the edge. Usually they define a star's size by its radius, the distance from its centre to the layer where the gas becomes thin enough that light can escape freely. This layer is called the photosphere. It's what we see as the visible surface of a star, even though it isn't solid at all. That definition works well for most stars, but for extremely large ones, especially red supergiants and hypergiants, the outer atmosphere can be so extended and diffuse that the exact boundary becomes difficult to pin down. The star's outer layers may be drifting outward, forming a kind of hazy envelope rather than a neat sphere. So right from the start, measuring size involves interpretation. Now, when astronomers describe a star as large, they're usually talking about radius, not mass. And those two things can be very different. Mass is simply how much material a star contains. Our Sun, for example, has a mass of about 2 trillion kilograms. That number is so large it's hard to imagine, but in astronomy it's a useful reference point. Scientists often compare other stars to the Sun using solar masses. A star with 10 times the Sun's mass is described as having 10 solar masses. There are stars with dozens, even hundreds of solar masses. These are among the most massive stars known, and they burn incredibly brightly and live very short lives. But here's the surprising part. Some of the largest stars in terms of diameter are not the most massive. In fact, many of them have less mass than some smaller, hotter stars. That might seem odd at first, but it makes sense if you picture the difference between a dense object and a fluffy one. A small steel ball can weigh more than a large balloon because the balloon is mostly empty space. Similarly, a giant star can be enormous in size but have relatively low density in its outer layers. Red supergiants are a good example. Their outer atmospheres are extremely expanded, stretched over enormous distances. The material there is thin, far thinner than anything we experience on Earth, yet gravity still holds it together as part of the star. So one way to define the largest star is by radius. The star with the greatest physical size from centre to outer layers. Another way would be by mass, the star containing the most matter. And yet another way would be by luminosity, the total amount of energy a star emits. Each of these measurements tells a different story. Luminosity, for instance, is a measure of brightness, but not the brightness we see with our eyes. astronomers distinguish between apparent brightness and intrinsic brightness. A nearby candle can look brighter than a distant lighthouse, but that doesn't mean it produces more light. To find a star's true luminosity, astronomers measure how bright it appears and combine that with its distance. Once they know how far away the star is, they can calculate how much energy it must be producing to appear as bright as it does from Earth. Some stars are incredibly luminous, millions of times brighter than the Sun. These stars may not always be the largest in diameter, but they are among the most energetic objects in the galaxy. So now we already have 3 different ideas of what largest could mean: largest radius, greatest mass, or highest luminosity. And that's before we even consider other factors like temperature, density, or lifetime. Another complication arises from the fact that stars change over time. Stars are not static objects, they evolve. A star that begins its life as a hot, compact object may expand enormously as it ages. The Sun itself will one day swell into a red giant, growing hundreds of times larger than it is now. It won't gain mass during that process. In fact, it will lose some. But its radius will increase dramatically. So when astronomers compare stars, they must also consider what stage of life each star is in. A massive young star might be smaller in diameter than an older star that has expanded late in its life, even though the younger star contains more material overall. There's also the question of measurement itself, which is more challenging than it might seem. Most stars are so far away that even the largest telescopes cannot see their disks clearly. They appear as points of light. So how do astronomers measure the size of something they cannot directly see? One method involves measuring the star's temperature and luminosity. There's a relationship in physics that connects a star's brightness, temperature, and radius. If you know how bright the star truly is and how hot its surface is, you can calculate how large it must be to produce that amount of energy. This method works well, but it depends on accurate measurements of distance, and distance is one of the hardest things to determine in astronomy. Even small uncertainties in distance can lead to large uncertainties in size. Another technique uses interferometry, a method where multiple telescopes are linked together to act like a much larger instrument. This allows astronomers to resolve the tiny disks of some nearby giant stars and measure their apparent diameter directly. Combined with distance measurements, this gives a more direct estimate of size. Even so, different methods sometimes give slightly different answers, and when you're dealing with stars hundreds or thousands of light years away, small errors can translate into huge differences in estimated size. That's one reason why the title of largest known star has changed several times over the years. New observations, improved instruments, and better data can shift the rankings. It's a bit like measuring mountains before the invention of precise surveying tools. Early explorers made estimates, but later measurements refined those numbers, sometimes significantly. Another interesting detail is that the largest stars are often not perfectly spherical. Their outer layers can be unstable, rising and falling in enormous convection currents. Some pulsate, expanding and contracting over time. Others lose material in slow stellar winds, creating shells of gas drifting into space. So when astronomers quote a radius for one of these stars, it is often an average value rather than a fixed boundary. There's also the matter of how we visualize size. Numbers alone can feel abstract, so astronomers often compare a giant star to our solar system. If a star's radius extends beyond the orbit of Mars, for example, that gives a more intuitive sense of scale. Imagine placing such a star where the Sun is. Mercury, Venus, Earth, and Mars would all be inside the star's outer layers. Jupiter might orbit just outside its surface, or perhaps even inside depending on the star. It's a striking way to picture these giants, and it helps make the concept of size more tangible. But even that comparison has limits, because the outer layers of a giant star are not like the surface of a planet. They are thin, diffuse, and in constant motion. A spacecraft entering those layers would not encounter a solid boundary, but rather a gradual thickening of hot gas. So the idea of being inside a star is more complex than it sounds. As we continue to explore the idea of stellar giants, it becomes clear that asking which star is the largest is not just about finding a single record holder. It's about understanding the different ways size can be defined, the different stages of stellar life, and the challenges of measuring objects across immense distances. And there's something quietly fascinating about that. The universe rarely offers simple answers to big questions. Instead, it invites us to look deeper, to refine our definitions, and to accept that sometimes the answer depends on how the question is asked. That's part of what makes astronomy such a patient science. It progresses step by step, observation by observation, each new measurement adding another piece to the puzzle. Understanding what largest means naturally leads to another question. How does a star grow so large at all, and what conditions allow such enormous objects to form in the first place? It might seem natural to assume that the bigger stars must begin their lives already enormous, as if the universe simply forms them that way from the start. But the reality is more gradual, and in some ways more interesting. Even the largest stars begin in places that are cold, dark, and quiet, regions of space where nothing at all appears to be happening. These regions are called molecular clouds. They are vast collections of gas and dust, often spanning dozens or even hundreds of light years. Most of the material is hydrogen, the simplest and most abundant element in the universe, mixed with traces of helium and heavier elements left behind by earlier generations of stars. If you could drift through one of these clouds, it would not feel like a cloud in the everyday sense. The gas is so thin that you would hardly notice it at all. The best vacuum chambers on Earth are denser than parts of these clouds, and yet, over enormous distances, even this faint material adds up to an immense mass. Within these clouds, gravity is always at work. It is a quiet, patient force, but it never stops. Tiny fluctuations in density, regions where the gas is just slightly thicker than its surroundings, begin to pull in more material. Over time, these regions grow denser still, drawing in gas from farther away. At first, the process is incredibly slow. It can take millions of years for a small clump to collapse into something recognizable as a forming star. But once the collapse begins in earnest, it accelerates. Gravity pulls harder as more mass gathers, and the core grows hotter and denser. Eventually, the temperature at the center becomes high enough for nuclear fusion to begin. Hydrogen nuclei start to fuse into helium, releasing energy in the process. That energy pushes outward, balancing the inward pull of gravity. When those two forces reach equilibrium, a star is born. That is the basic story of star formation, and it applies to stars of all sizes. But forming a truly massive star, the kind that can later swell into a gigantic red supergiant or hypergiant, requires something more. It requires an enormous reservoir of material. In most parts of a molecular cloud, there simply isn't enough mass in one place to form a very large star. The collapsing region fragments into smaller clumps, each forming a modest star rather than one giant one. This fragmentation is one of the biggest challenges in understanding how stellar titans form. Astronomers have learned that the largest stars tend to form in the densest and most active star-forming regions, places where huge amounts of gas are packed together and where many stars are forming at once. These regions are sometimes called stellar nurseries, and they can be spectacular sights, glowing with light from newborn stars that illuminate the surrounding gas. One famous example is the Orion Nebula, visible even to the naked eye under dark skies. Inside it, hundreds of young stars are forming, and among them are some far larger than the Sun. Yet even Orion is modest compared to the most extreme star-forming regions in the galaxy, where clusters of massive stars are born together in tight groups. In these crowded environments, gravity has a better chance of gathering enough material to form a truly massive star. Gas flows inward from all directions, feeding the growing protostar at the center. But there is a problem. As a forming star becomes more massive, it also becomes brighter. That brightness creates intense radiation pressure, a force produced by the light streaming outward. For a very massive protostar, this radiation can push away the surrounding gas, effectively shutting off the supply of material and limiting how large the star can grow. For a long time, astronomers wondered whether this radiation pressure might prevent stars from growing beyond a certain size altogether. Yet observations clearly show stars with dozens or even more than 100 times the Sun's mass, so nature must have found a way around this barrier. The answer seems to involve disks and jets. As gas falls toward a forming star, it often forms a rotating disk rather than collapsing directly inward. Material spirals through this disk and onto the star, while powerful jets of gas are launched along the star's poles, carrying away excess energy and angular momentum. These jets may help clear pathways that allow gas to continue flowing inward despite the intense radiation. Instead of blowing material away in all directions, the radiation escapes more easily along the poles, while the disk continues feeding the star. It's a delicate balance, but under the right conditions it allows stars to grow to enormous masses. Another factor that helps is the sheer density of some star-forming regions. When gas is packed closely together, gravity can overpower radiation pressure more effectively. The infalling material simply has too much momentum to be pushed away easily. So in these rare environments, stellar titans can form. Once such a star ignites, its life is very different from that of a smaller star like the Sun. Massive stars burn their fuel at an astonishing rate. The greater the mass, the higher the pressure and temperature in the core, and the faster nuclear fusion proceeds. A star 10 times the mass of the Sun may shine thousands of times more brightly. A star 50 times the Sun's mass may burn so intensely that its entire lifetime lasts only a few million years, a brief moment compared to the Sun's expected lifespan of about 10 billion years. These massive stars begin their lives as hot blue stars, compact compared to the enormous giants they may later become. Their surfaces are blisteringly hot, tens of thousands of degrees, and their light is fierce and energetic. But over time, changes begin deep in the core. As hydrogen is consumed, the balance between gravity and pressure shifts. The core contracts and heats up, while the outer layers respond by expanding outward. The star begins to swell. For the most massive stars, this expansion can be dramatic. The outer layers drift farther and farther from the centre, cooling as they spread out, turning the star redder in colour and vastly larger in size. This is how many of the largest stars in the universe reach their enormous diameters. They are not born enormous in size, they grow into it as they age, and the scale of that growth is difficult to overstate. Imagine a star that begins its life perhaps 10 or 20 times larger than the Sun. Over time, it expands until its radius is hundreds, or even more than 1,000 times greater than the Sun's. Its outer atmosphere becomes so extended that it would engulf the inner planets if placed in our solar system. Yet despite this vast size, the star's outer layers can be extraordinarily thin. The density there may be lower than the best vacuums we can produce on Earth. The star becomes like a glowing fog spread over an immense volume, still bound together by gravity, still shining, but stretched to an almost unimaginable scale. There is another interesting aspect of massive star formation, one that adds a sense of continuity to the story of the universe. The material that forms these stars is not pristine hydrogen left untouched since the beginning of time. It has been enriched by earlier generations of stars. Long ago, other massive stars lived and died, exploding as supernovae and scattering heavier elements into space. Those elements mixed into molecular clouds, becoming part of new stars, planets, and eventually living things. So when a stellar titan forms, it carries within it the ashes of earlier stars, material that has been recycled through cosmic history. In that sense, every giant star is part of a long chain of creation and transformation, each generation building on the last. Astronomers have also found that the largest stars rarely form in isolation. They are often members of clusters, surrounded by dozens or hundreds of smaller stars born from the same cloud. These clusters can be crowded places with stars passing relatively close to one another, gravitationally interacting, and sometimes even exchanging material. In such environments, there is also the possibility of stellar mergers. Two massive stars in a tight binary system may spiral together and combine, forming a single even larger star. This process is thought to play a role in creating some of the most extreme stars known, though it is still an area of active research. The idea that a giant star might be the product of two stars merging adds another layer to the story. Not all stellar titans are simply born large. Some may grow large through dramatic encounters long after their initial formation. All of this helps explain how stars can become massive enough to later expand into the enormous red supergiants and hypergiants that compete for the title of largest known star. Yet even with all these processes, there seem to be limits. Observations suggest that stars above a certain mass, perhaps around 150 to 200 times the mass of the Sun, are extremely rare or may not form at all under most conditions. Radiation pressure and stellar winds become so strong that they blow away material faster than it can be gathered. So nature appears to set an upper boundary, not a strict wall, but a region where forming even larger stars becomes increasingly difficult. Still, within those limits, the universe manages to produce stars of astonishing scale, stars that begin in cold, dark clouds and end as glowing giants visible across thousands of light years. And once these titans have formed and begun to age, their story continues in ways that are just as fascinating as their birth. Long before astronomers had precise instruments or detailed theories, people noticed that some stars looked different from others. Most stars appear as sharp, steady points of white or bluish light, but a few stand out immediately, glowing with a deeper, warmer colour. They appear reddish or orange, and even to the naked eye they seem somehow softer, as if their light carries a different character. For centuries, no one knew exactly why these stars look this way. Today, we understand that many of them belong to a class called red supergiants, and these are among the first stars that truly deserve to be called giants in every sense of the word. To understand what makes a red supergiant special, it helps to think about how stars change over time. A star spends most of its life in a stable phase called the main sequence, steadily fusing hydrogen into helium in its core. During this period, the star's size and brightness remain relatively constant. Our Sun is in this stage right now, and it will remain there for billions of years. But massive stars live very different lives from smaller ones. They burn through their hydrogen quickly, sometimes in just a few million years. When the hydrogen in the core begins to run low, the balance between gravity and pressure shifts. The core contracts, heating up further, while the outer layers begin to expand, and this expansion is not subtle. The outer layers of the star swell outward enormously, growing hundreds of times larger than before. At the same time, the surface temperature drops, which changes the colour of the light the star emits. Instead of shining white or blue, the star begins to glow red or orange. That is how a red supergiant is born, not from the beginning, but as a later stage in the life of a massive star. What makes these stars remarkable is not just their size, but the scale of that expansion. Some red supergiants are so large that if one replaced the Sun, its outer atmosphere would extend beyond the orbit of Mars, sometimes even approaching Jupiter's orbit. It's difficult to picture such a size, so it helps to use comparisons. Imagine the Sun as a sphere about 1 metre across. In that scale, Earth would be a tiny bead orbiting more than 100 metres away. Now imagine replacing that 1 metre sphere with something the size of a large building. The distances of the inner planets would suddenly feel very small, swallowed by the star's enormous outer layers. Yet despite their vast size, red supergiants are not particularly dense. Their outer atmospheres are extremely thin, far thinner than any air we experience on Earth. The material there is spread over such a large volume that the star becomes, in a sense, a glowing fog bound together by gravity. If you could somehow travel into the outer layers of a red supergiant, you wouldn't encounter a sharp surface. Instead, you would pass gradually into thicker and hotter gas, the light around you glowing in shades of deep orange and red, the density slowly increasing as you moved inward. Another surprising feature of red supergiants is how unstable they can be. Unlike the Sun, whose surface appears relatively calm on large scales, red supergiants are turbulent places. Massive convection currents churn through their outer layers. These currents are like boiling cells of gas, but on a scale almost impossible to imagine. On the Sun, convection cells are roughly the size of continents. On a red supergiant, a single convection cell can be larger than the orbit of Earth. Vast regions of hot gas rise, cool, and sink again, slowly circulating over months or years. This immense convection can cause the star's brightness to vary slightly over time. It can also lead to the ejection of material into space. Red supergiants often lose mass through slow, steady stellar winds, streams of gas drifting away from the star and forming extended shells of dust and molecules around it. These shells can be enormous, stretching across distances comparable to the size of our solar system or larger. Over time, the star sheds a significant fraction of its mass in this way, enriching the surrounding space with heavy elements. And those elements matter. They will one day become part of new stars, planets, and perhaps even life. When astronomers observe red supergiants, they often focus on nearby examples that can be studied in detail. One of the most famous is Betelgeuse, a bright red star in the constellation Orion. Even without a telescope, it's easy to spot on a clear night, glowing with a distinct reddish hue. Betelgeuse is enormous, hundreds of times larger than the Sun, and it has been studied extensively. In recent years, it even dimmed noticeably for a period, leading to speculation about what might be happening. Eventually, astronomers concluded that part of the dimming was caused by a cloud of dust the star itself had expelled, temporarily blocking some of its light. This event offered a reminder that red supergiants are dynamic, changing objects. They are not static spheres, but living, evolving systems, shedding material, pulsating, and slowly approaching the final stages of their lives. Another well-known red supergiant is Antares, in the constellation Scorpius. Like Betelgeuse, it shines with a deep red colour and is vastly larger than the Sun. Observations have revealed enormous plumes of gas rising from its surface, extending outward for distances comparable to the size of our solar system. These observations have only become possible in recent decades, as telescopes and imaging techniques have improved. For much of human history, red supergiants were simply bright red points in the sky, their true nature hidden by distance. Today, astronomers can map their surfaces, study their atmospheres, and even observe the motions of gas within their outer layers. One of the reasons red supergiants become so large lies in the physics of energy transport inside the star. As the core contracts and heats up, fusion begins in shells surrounding the core rather than only at the centre. This releases enormous amounts of energy, which pushes the outer layers outward. Gravity still holds the star together, but the balance shifts. The outer layers expand until a new equilibrium is reached, one where the star is much larger and cooler at the surface than before. But this expanded state is not permanent. Red supergiants are living on borrowed time. Their cores continue to evolve, fusing heavier and heavier elements in a sequence that eventually leads to iron, an element that cannot release energy through fusion. When that point is reached, the core can no longer support itself, and the star's life ends in a supernova, one of the most powerful explosions in the universe. Yet that dramatic ending lies ahead in the story. For now, what matters is that red supergiants represent the first stage where stars truly become colossal in size, large enough to dominate comparisons and challenge our sense of scale. They are not the absolute largest stars known, but they are the gateway to understanding stellar giants. Many of the record-holding stars, the ones sometimes proposed as the largest of all, belong to related categories that push the same processes even further. There's also something quietly fascinating about the way red supergiants appear to us from Earth. Despite their immense size, they look small in the sky, mere points of light. Distance compresses everything. A star that could engulf our entire solar system appears no larger than a grain of sand held at arm's length. It's a reminder of how vast the universe truly is. Size alone doesn't determine what we see. Distance matters just as much, and distance also complicates measurement. Determining the radius of a red supergiant requires knowing how far away it is, how bright it truly is, and how hot its surface is. Small uncertainties in any of these measurements can lead to large differences in the estimated size. That's one reason why the list of the largest stars is constantly changing. As new observations refine distances and temperatures, estimates of radius shift. A star once thought to be the largest may turn out to be smaller than previously believed, while another takes its place. Science progresses in this quiet, careful way, refining numbers, checking assumptions, and gradually improving our understanding. There is also the question of how large a star can become before it becomes unstable. Red supergiants are already close to the limits of what a star can sustain. Their outer layers are only loosely bound by gravity, and strong stellar winds steadily carry material away. Some of the most extreme stars lose mass at astonishing rates, shedding the equivalent of Earth's mass every few years or decades. Over time, this mass loss can significantly alter the star's evolution. So even as these stars expand to enormous sizes, they are also slowly dissolving, their outer layers drifting into space. That dual nature, immense yet fragile, is part of what makes red supergiants so interesting to study. They represent both the peak of stellar expansion and the beginning of the end. By the time astronomers had begun to understand red supergiants, it already felt as though the universe had reached the upper limits of what a star could be. A star hundreds of times larger than the Sun, with an atmosphere so vast it could swallow entire planetary systems, seemed like a natural extreme. For a while, many researchers assumed that red supergiants represented the largest stable stage a star could reach. But as telescopes improved and surveys of the galaxy became more detailed, something unexpected began to appear. There were a few stars that didn't quite fit the categories astronomers had established. They were brighter than typical supergiants, losing mass at extraordinary rates, surrounded by immense shells of gas, and in some cases even larger in radius than the already enormous red supergiants. These rare stars were eventually given a name that reflected their extraordinary nature: hypergiants. The term sounds dramatic, but in astronomy it has a fairly specific meaning. A hypergiant is a star of extremely high luminosity that is also unstable, often shedding material into space and showing signs of rapid evolution. These stars are among the most luminous objects in the galaxy, sometimes shining hundreds of thousands or even millions of times brighter than the Sun. And while not all hypergiants are the largest in physical size, many of the biggest stars known belong to this category. To understand what sets hypergiants apart, it helps to think about the balance that keeps any star stable. A star exists because two forces are in equilibrium. Gravity pulls inward, trying to compress the star, while the energy produced by nuclear fusion pushes outward. As long as these forces remain balanced, the star remains stable. But in the most massive stars, this balance becomes delicate. The outward pressure from radiation becomes so strong that it begins to rival gravity itself. The star is, in a sense, only loosely bound together. In hypergiants, this delicate balance leads to instability. The outer layers can expand, contract, and even be blown away in massive eruptions. Some hypergiants are surrounded by enormous clouds of gas that were once part of the star itself, expelled over thousands of years. These eruptions are not like the explosions that end a star's life. They are slower, more gradual events, sometimes called stellar outbursts. during which the star sheds part of its outer atmosphere into space. If you could observe a hypergiant up close over long periods of time, you would see a star that is constantly changing, its brightness fluctuating, its atmosphere shifting, and its surrounding environment slowly filling with drifting clouds of gas and dust. Another feature that distinguishes hypergiants is their immense luminosity. Some of them are so bright that the energy pouring out from their surfaces drives powerful stellar winds, streams of particles flowing outward at high speeds. These winds can carry away vast amounts of material over the star's lifetime. In fact, some hypergiants lose mass so rapidly that they may shed several times the mass of the Sun before they reach the end of their lives. It's a strange thought, a star gradually dissolving into space, leaving behind a glowing envelope of gas that continues to expand long after the star itself has changed or disappeared. One of the most famous examples of a hypergiant is Eta Carinae, a star system located thousands of light-years away. In the 19th century, Eta Carinae suddenly brightened dramatically, becoming one of the brightest stars in the sky for a time. This event, known as the Great Eruption, expelled an enormous amount of material into space, forming a vast cloud now called the Homunculus Nebula. Today, that cloud continues to expand, glowing in the light of the star that created it. Observations show that Eta Carinae is still unstable, still shedding mass, and still evolving. Events like this remind astronomers that hypergiants are not calm, steady stars. They are living on the edge of stability, their immense luminosity and mass pushing them toward dramatic changes. Not all hypergiants are as luminous as Eta Carinae, and not all undergo such spectacular eruptions. Some are red hypergiants, cooler in temperature but enormous in size. Others are yellow or blue hypergiants, hotter and often even more luminous, though sometimes smaller in radius. This variety shows that hypergiants are not defined by size alone. They are defined by their extreme properties, their luminosity, instability, and rapid evolution. Still, some of the largest stars known are red hypergiants, stars whose outer layers have expanded to astonishing dimensions. These stars often appear deep red in colour, their vast atmospheres cool compared to hotter stars, but stretched over such enormous distances that their total brightness remains immense. Measuring the size of these stars is challenging. Their outer layers are often irregular, with vast plumes of gas extending outward. The boundary between the star and the surrounding space becomes blurred, making it difficult to determine exactly where the star ends. Astronomers must rely on careful measurements of temperature, brightness, and distance, along with models of stellar atmospheres, to estimate their radii. And because these stars are so distant, and their atmospheres so complex, the uncertainties can be significant. That's one reason why the identity of the largest known star can change as new observations are made. A revised distance measurement or a better understanding of a star's atmosphere can alter its estimated size, sometimes by large amounts. Despite these uncertainties, certain names appear again and again in discussions of the largest stars. Stars like Ui Scuti, Vibi Canis Majoris, and others have been proposed as candidates for the largest known, each with estimated radii that stretch far beyond anything we can easily imagine. Some of these stars are so large that if placed at the centre of our solar system, their outer layers would extend beyond the orbit of Jupiter or even Saturn. Light would take hours to travel from one side of the star to the other, and yet these stars are not permanent. Their immense size is only a phase, a brief moment in their overall lifetimes. The same processes that cause them to expand also lead to their eventual collapse and explosion. Hypergiants live fast and die young by stellar standards. A star like the Sun may shine for 10 billion years, but a hypergiant may last only a few million years before reaching the end of its life. That brevity adds a certain poignancy to their existence. These are the giants of the galaxy, blazing with incredible brightness, yet their time is short. There is also another interesting detail about hypergiants. Because they are so luminous, they influence their surroundings in powerful ways. Their radiation ionizes nearby gas, causing nebulae to glow. Their stellar winds shape the interstellar medium, carving bubbles and shells in the surrounding material. In star-forming regions, massive stars, including hypergiants, can even trigger the formation of new stars by compressing nearby clouds of gas. In this way, the life of one giant star can help give birth to the next generation. So these stars are not just isolated objects. They are part of a larger cycle, shaping and being shaped by their environment. It's also worth noting that hypergiants are extremely rare. In a galaxy containing hundreds of billions of stars, only a tiny fraction are hypergiants. They are the exceptions, the extremes, the stars that push the limits of what gravity and nuclear fusion can sustain. That rarity makes them valuable to study. Each hypergiant offers clues about the upper limits of stellar mass, luminosity and size. By observing them, astronomers learn not only about the stars themselves, but also about the physics that governs all stars. As observations improve, astronomers continue to search for stars that might be even larger, even more luminous, or even more extreme. And occasionally, a new candidate emerges, a star whose estimated size challenges previous records and reignites the question of which star truly deserves to be called the largest. When astronomers talk about the largest stars, a few names appear again and again, almost like familiar landmarks in an enormous landscape. These are the stars that have, at one time or another, been considered the biggest known, or at least among the biggest. Each one has its own story, its own uncertainties, and its own place in the gradual effort to understand just how large a star can become. One of the most frequently mentioned is UY Scuti. This star lies thousands of light-years away in the constellation Scutum, a faint region of the sky that most people would never notice without a telescope. Yet hidden there is a star so large that its estimated radius has made it one of the most widely cited examples of a stellar giant. To appreciate what that means, it helps to step away from numbers for a moment and think in terms of distance. If UY Scuti were placed at the centre of our solar system, its outer atmosphere would extend beyond the orbit of Jupiter. That's not a casual comparison or a poetic exaggeration. It's a scale derived from measurements of brightness, temperature and distance, combined with models of stellar structure. Light itself would take several hours to travel from one side of UY Scuti to the other. Imagine standing on one side of such a star and sending a beam of light straight across. Hours would pass before that light reached the far edge. That's the kind of scale astronomers are dealing with when they talk about the largest stars. Yet even with such enormous estimates, astronomers remain cautious. Measuring the radius of a star like UY Scuti is not straightforward. The outer layers are diffuse, and the exact boundary of the star depends on how one defines the visible surface. Different models and different measurements can yield slightly different results, sometimes enough to shift the ranking among the largest stars. So while UY Scuti is often cited as one of the largest known stars, scientists usually add a quiet phrase based on current estimates. That phrase appears often in astronomy, and it reflects the reality that knowledge improves over time. Another famous giant is VY Canis Majoris, a red hypergiant located in the constellation Canis Major. For many years, this star was thought to be the largest known. Early measurements suggested an extraordinary radius, and images of the surrounding region revealed vast clouds of gas and dust, material that the star itself had expelled. VY Canis Majoris is an unstable star, losing mass at a tremendous rate. Its outer layers are not smooth or symmetrical. Instead, enormous plumes of gas extend outward, forming a complex and irregular envelope. Observations show knots and arcs of material drifting away, illuminated by the star's intense light. This instability complicates the measurement of its size. Where exactly does the star end and the surrounding cloud begin? The boundary is not sharp. Over time, improved observations led astronomers to revise the estimated size of VY Canis Majoris downward somewhat, though it remains one of the largest and most luminous stars known. The story of VY Canis Majoris is a good example of how science progresses. Early estimates suggested one value. Later observations refined that value. The star itself did not shrink. Rather, our understanding became more precise. There is something reassuring about that process. It shows that knowledge grows gradually, shaped by better instruments, better data, and careful analysis. Another name that often appears in discussions of stellar giants is OHG 64, a red supergiant located in the Large Magellanic Cloud, a neighbouring galaxy visible from the southern hemisphere. This star is particularly interesting because it is surrounded by a thick disk of dust, which absorbs and re-emits much of its light in the infrared. That dust makes the star difficult to study in visible wavelengths, but infrared observations reveal its enormous size and luminosity. WOHG 64 is not only large but also heavily obscured, wrapped in a cocoon of material it has shed over time. Stars like this remind us that the larger stars are often messy, surrounded by the debris of their own evolution. They are not clean, perfect spheres, but dynamic systems interacting with their surroundings. There are other contenders as well, each with its own peculiarities. Some are slightly smaller in radius but more massive. Others are extraordinarily luminous but somewhat more compact. The exact ranking depends on which measurement one emphasizes and how uncertainties are handled. Astronomers sometimes joke that the title of largest star is like a rotating trophy, passed from one candidate to another as new data arrives. But beyond the competition for records, what truly matters is what these stars teach us about the limits of stellar structure. One of the key lessons is that there are physical limits to how large a star can become. As a star expands, its outer layers become more weakly bound by gravity. Radiation pressure and stellar winds carry material away. Pulsations and convection stir the atmosphere, sometimes ejecting entire shells of gas. At a certain point, the star cannot maintain its enormous size for long. It begins to lose mass more rapidly, or its internal structure changes, leading to contraction or to the final stages of its evolution. So the largest stars we see are often in brief phases of their lives, expanded to immense sizes but destined to change relatively soon on cosmic timescales. There is also the question of distance, which plays a crucial role in determining size. To estimate a star's radius, astronomers must know how far away it is. Even a small error in distance can produce a large error in the calculated size. Measuring distance in astronomy is a complex process, involving methods such as parallax, standard candles, and spectroscopic analysis. Each method has its own uncertainties, and for very distant stars those uncertainties can be significant. This means that the estimated size of a giant star is always accompanied by an uncertainty range. A star might be listed as having a radius between, say, 1,000 and 1,500 times that of the Sun. Within that range, its exact ranking among other giant stars may be uncertain. That uncertainty is not a flaw in science, it is part of the process. Measurements improve, error bars shrink, and our picture of the universe becomes clearer over time. Another fascinating aspect of these famous giants is how they appear to us from Earth. Despite their immense size, they are so far away that even the largest telescopes see them as tiny disks or points of light. Only in a few cases, using advanced techniques like interferometry, have astronomers been able to resolve the surfaces of nearby giant stars. Even then, the images are not like photographs of planets. They are often blurry, showing uneven brightness, large convection cells, and irregular shapes. These observations reveal that giant stars are not perfectly spherical. Their surfaces are constantly in motion, shaped by enormous currents of hot gas rising and falling. In some cases, astronomers have even observed giant stars changing shape slightly over time, their atmospheres swelling or contracting as internal processes shift. It's a reminder that stars are not static objects frozen in time. They are dynamic, evolving, and in the case of the largest ones, often unstable. There is also something quietly humbling about the way these stars challenge our sense of scale. When we learn that a star is 1,000 times larger than the Sun, the number is impressive, but it can still feel abstract. But when we imagine the orbit of Earth lying deep inside the star's atmosphere, the scale becomes more tangible. It changes the way we think about our own place in the universe. The Sun, which seems so large and powerful to us, is modest compared to these giants, and yet the Sun itself is only one star among hundreds of billions in our galaxy alone. Another interesting point is that many of the largest stars are not visible to the naked eye. Some are too distant, others are obscured by dust. The brightest stars in the sky are not necessarily the largest, and the largest are not necessarily the brightest from our perspective. This means that the true giants of the universe are often hidden, known only through careful observation with powerful telescopes. As astronomers continue to survey the galaxy and beyond, new candidates occasionally emerge. Improved infrared observations, better distance measurements, and more detailed models of stellar atmospheres all contribute to refining our understanding. It is entirely possible that even larger stars exist, waiting to be discovered or measured more accurately. Among all the enormous stars astronomers have studied, there are a few that seem to push the limits not just of physics, but of imagination itself. These are the stars that make even seasoned researchers pause for a moment, double-check the data, and ask quietly whether the numbers truly make sense. Because sometimes the scale involved is so extreme that it feels almost unreal, even to those who work with such measurements every day. It is in this context that astronomers sometimes use informal names or nicknames when discussing particularly immense stars. One of those nicknames, used occasionally in articles and discussions, is Behemoth. It is not an official designation in the way catalogue numbers are, but it captures something important. It reflects the feeling people get when confronted with a star whose sheer size stretches the limits of what seems possible. To understand why such a name feels appropriate, it helps to take a slow, careful look at what makes one of these stars so extraordinary. When astronomers identify a candidate for one of the largest known stars, they begin by measuring several key properties. The first is luminosity, the total energy the star emits. The second is surface temperature, which can be estimated from the star's spectrum, the pattern of colours in its light. And the third is distance, usually determined through a combination of parallax motion studies and comparisons with known stellar populations. Once those values are known, astronomers can estimate the star's radius. And sometimes that radius turns out to be astonishing. For a star like the one sometimes referred to as Behemoth, the estimated radius may be well over 1,000 times that of the Sun. That number alone is difficult to grasp, so it helps to translate it into something more familiar. If such a star were placed at the centre of our solar system, its outer layers would not merely reach the orbit of Mars. They would extend past the asteroid belt beyond Jupiter, perhaps approaching Saturn depending on the estimate used. The inner planets would not simply orbit inside the star, they would have formed, if they could form at all, deep within its atmosphere. Now pause for a moment and imagine that scene, not dramatically, just quietly and carefully. Picture the orbit of Earth, the path our planet follows each year around the Sun. Now imagine that entire orbit lying inside a star surrounded by glowing, slowly drifting layers of gas. The sky would not be dark. It would be filled with a dim, reddish light. The glow of a vast atmosphere extending in all directions. It is an image that feels almost impossible, yet it follows directly from the measurements astronomers make. What makes stars like this even more fascinating is that their immense size does not mean they are especially dense. In fact, the outer layers of such stars are extraordinarily thin. The density of the gas near the surface can be far lower than the air we breathe, far lower even than the best vacuums produced in laboratories on Earth. So although the star is enormous in size, it is also diffuse, its mass spread over an immense volume. This combination of vast size and low density gives these stars a peculiar character. They are not solid spheres or even sharply defined balls of gas. They're more like enormous glowing atmospheres, gently held together by gravity, their outer edges fading gradually into space. And those outer layers are far from calm. Inside a giant star, energy generated in the core travels outward, and much of that energy is transported by convection, the slow rising and falling of hot gas. In the Sun, convection creates cells roughly the size of continents. In a star the size of Behemoth, a single convection cell can be larger than the orbit of Earth. These vast currents rise and fall over timescales of months or years, causing the star's brightness to fluctuate slightly. Observations of giant stars often reveal irregular variations in light, a sign of the immense motions taking place beneath the surface. Another remarkable feature of such stars is the way they lose mass. The outer layers are only loosely bound by gravity, and powerful stellar winds carry material outward into space. Over time, the star sheds enormous quantities of gas, forming a surrounding envelope of dust and molecules. In some cases, this envelope becomes so thick that it obscures the star in visible light. Astronomers must then observe it in infrared wavelengths, where the dust becomes transparent and the star's glow can still be detected. This is often how the largest stars are studied, through infrared observations that reveal their true luminosity and size. There is also the question of how long a star like this can remain so large. The answer is not very long, at least in cosmic terms. The largest stars live fast and burn through their fuel rapidly. The stage in which a star expands to such enormous dimensions may last only a few tens of thousands of years, a brief moment compared to the millions of years the star has already lived. So when we observe a star at this stage, we are seeing it during a relatively short chapter of its life. That fact adds a quiet sense of rarity to the observation. The universe contains vast numbers of stars, but only a tiny fraction are caught in this brief phase of extreme expansion. Another aspect that challenges our sense of scale is the sheer distance to these stars. Many of the largest known stars are thousands or even tens of thousands of light years away. The light we see from them began its journey long before the modern world took shape, long before electric lights or airplanes or satellites. When astronomers measure such a star, they are studying an object not as it is now, but as it was long ago. The present state of the star, whatever it may be, will not be known until its light reaches us, perhaps thousands of years in the future. There is something quietly humbling about that. We are always looking into the past, always receiving messages carried by light across immense distances. And yet, despite that distance, the scale of these stars still reaches us through careful measurement and patient observation. Sometimes, when astronomers first calculate the radius of a candidate for the largest star, the result seems almost too large to believe. Researchers check the data again, refine the distance estimates, and compare the results with models of stellar atmospheres. Occasionally, the estimate is revised downward. Other times, it holds up under scrutiny. This careful process is why the identity of the largest known star is never fixed forever. New measurements, improved instruments, and better models can change the ranking. But regardless of which star currently holds the record, the existence of such giants tells us something fundamental about the universe. It shows that nature is capable of creating structures on scales far beyond everyday experience, yet governed by the same physical laws that operate everywhere else. Gravity, pressure, radiation, and nuclear fusion. The same processes that shape our sun also shape stars 1,000 times larger. There is also an interesting contrast between size and brightness. Some of the largest stars are not the brightest in the sky. Their enormous size is balanced by relatively cool surface temperatures, which means their light is spread over a vast area and peaks in the red or infrared part of the spectrum. So a star that could engulf our solar system might appear faint to the naked eye, visible only through telescopes. That contrast between immense size and modest appearance is part of what makes these stars so intriguing. They remind us that the universe does not always present its greatest wonders in obvious ways. Another point worth considering is how such a star would appear if viewed from nearby. From a distance comparable to Earth's orbit, the star's disk would fill a huge portion of the sky. The surface would not look smooth. It would appear mottled and uneven, with enormous convection cells rising and falling slowly, glowing in deep shades of red and orange. The surrounding space would be filled with drifting clouds of gas, illuminated by the star's light. It would be a quiet, slow-moving scene, not violent or explosive, but vast and steady, the motions unfolding over months or years rather than seconds. Thinking about such scenes can change the way we think about time as well as size. Processes that seem slow to us, the movement of gas over years, the gradual loss of mass over centuries, are part of the ordinary life of these stars. They live on scales of both space and time that are difficult for the human mind to grasp, yet still understandable with patience and careful thought. And that is perhaps the most remarkable thing about studying stars like this. They stretch our sense of scale, but they do not place themselves beyond understanding. Step by step, measurement by measurement, astronomers piece together a picture of objects so distant and so immense that they once would have seemed unknowable. How do astronomers determine the size of a star whose surface cannot be seen clearly, whose distance is measured across thousands of light years, and whose atmosphere is constantly shifting? At first glance, measuring the size of a star might seem like it should be straightforward. After all, we measure the sizes of objects all the time. A building can be measured with a tape measure, a mountain with surveying instruments, even planets with radar and telescopes. But stars are different. They are incredibly far away, and most of them appear as nothing more than tiny points of light, even in powerful telescopes. So the question naturally arises, if we cannot clearly see the surface of most stars, how do astronomers figure out how large they are? The answer is that measuring distant stars is a bit like solving a puzzle. Instead of observing one obvious feature, astronomers combine several pieces of information, each one giving part of the answer. When those pieces are put together carefully, they reveal the size of something that cannot be measured directly. One of the most important pieces of that puzzle is distance. Before astronomers can determine how large a star truly is, they must know how far away it is. Without distance, brightness alone can be misleading. A nearby candle looks brighter than a distant lighthouse, but that doesn't mean it produces more light. Stars behave the same way. A star that appears faint might actually be extremely luminous, but very far away. So measuring distance is the first step. For relatively nearby stars, astronomers use a method called parallax. This technique relies on observing how a star appears to shift slightly against the background of more distant stars as Earth moves around the Sun. The shift is tiny, often less than a fraction of a second of arc, but with precise instruments it can be measured. The principle is similar to holding out your thumb and looking at it with one eye then the other. Your thumb appears to move against the background, and from that shift, you can estimate how far away it is. Astronomers use the same idea, but on a much larger scale and with far greater precision. Modern space telescopes, such as the Gaia mission, have measured the distances to millions of stars using parallax, providing incredibly accurate data. These measurements form the foundation for much of what we know about stellar sizes. However, many of the largest stars are extremely distant, sometimes thousands or tens of thousands of light years away. At those distances, parallax becomes very difficult to measure. The apparent shift is simply too small. In such cases, astronomers turn to other methods. One common approach involves studying the star's spectrum, the pattern of colours in its light. By spreading starlight into a spectrum, astronomers can determine the star's temperature, composition, and sometimes its luminosity class, which indicates how bright it truly is compared to other stars of similar type. Once they have an estimate of the star's intrinsic brightness, they compare it to how bright it appears from Earth. The difference between those two values gives an estimate of distance. This method, known as spectroscopic distance, is less direct than parallax but still very useful, especially when combined with other observations. After distance is known, the next step is to determine the star's luminosity, the total amount of energy it emits. This involves measuring how much light reaches Earth across different wavelengths, including visible light and infrared. Infrared observations are particularly important for giant stars because many of them are surrounded by dust that absorbs visible light. That dust re-emits energy in the infrared, and telescopes designed to observe infrared radiation can detect this glow and provide a more complete picture of the star's output. Once astronomers know how luminous a star is and how hot its surface is, they can calculate its radius using a physical relationship known as the Stefan-Boltzmann law. This law connects luminosity, temperature, and surface area. In simple terms, a cooler star must be larger than a hotter one if both emit the same total energy. This calculation provides an estimate of the star's size, even when the star cannot be resolved directly. Still, astronomers prefer direct measurements whenever possible, and in some cases they have found ways to achieve them. One of the most powerful techniques for measuring the apparent size of stars is interferometry. This method involves linking multiple telescopes together so that they act like a single, much larger telescope. By combining the light collected at different points, astronomers can achieve extremely high resolution, enough to measure the tiny disks of some nearby giant stars. Interferometry has allowed scientists to measure the diameters of stars such as Betelgeuse and Antares, revealing not only their size but also details of their surfaces. These observations have shown that giant stars often have uneven brightness, enormous convection cells, and irregular shapes. The images produced by interferometry are not like ordinary photographs. They require complex data processing and careful interpretation, but they provide valuable information that cannot be obtained in any other way. Even with these techniques, uncertainties remain. Measuring the size of a giant star is complicated by the nature of its atmosphere. Unlike a planet which has a well-defined surface, a star's outer layers gradually thin out into space. The photosphere, the layer where most visible light is emitted, is used as a reference point, but in giant stars this layer can be extended and irregular. In some cases, different wavelengths of light originate from slightly different depths in the atmosphere, which can make the star appear larger or smaller depending on how it is observed. Astronomers must account for these effects when interpreting their measurements, using models of stellar atmospheres to estimate where the effective surface lies. Another factor that complicates measurements is variability. Many giant stars pulsate, expanding and contracting over time. Their brightness changes slightly, and their radius can vary as well. Observations taken at different times may therefore give different results, and astronomers must average measurements over long periods to obtain reliable values. There is also the challenge of interstellar dust. Light travelling from a distant star to Earth passes through clouds of gas and dust that can absorb or scatter certain wavelengths. This process, called extinction, can make a star appear dimmer and redder than it truly is. To correct for this effect, astronomers study the properties of the intervening dust and adjust their measurements accordingly. This requires observations at multiple wavelengths and careful modelling of how dust affects starlight. It is a detailed and patient process, but it allows scientists to reconstruct the true brightness and temperature of distant stars with remarkable accuracy. Sometimes, astronomers also use binary systems to measure stellar properties. If a giant star has a companion star orbiting it, the motion of the two stars can reveal their masses and other characteristics. These measurements provide valuable constraints that improve estimates of size and luminosity. In other cases, astronomers study the expansion of gas shells around giant stars. By measuring the speed at which the gas is moving and the apparent size of the shell, they can estimate how long ago the material was ejected and how large the star must have been at the time. All of these methods, distance measurements, spectral analysis, interferometry, infrared observations, and modelling, work together to build a picture of stars that are far too distant to touch or measure directly. It is a bit like assembling a portrait from scattered clues. Each observation adds a piece, and over time the image becomes clearer. What makes this process especially fascinating is that it is always improving. New telescopes, both on Earth and in space, provide sharper images and more precise data. Instruments sensitive to different wavelengths reveal details that were once hidden. Computer models become more sophisticated, allowing astronomers to simulate stellar atmospheres with increasing realism. As a result, the estimated sizes of some giant stars have changed over the years, sometimes significantly. A star once thought to be the largest known might be revised downward when a more accurate distance measurement becomes available. Another star might be found to be larger than previously believed. This constant refinement is not a sign of uncertainty in the negative sense. It is the normal process of science, a gradual narrowing of possibilities as better information becomes available. There is also something quietly remarkable about the patience involved. The light from some of these stars has travelled for thousands of years to reach us. Astronomers then spend years or decades studying that light, refining measurements and checking results. The timescales involved, both in the stars themselves and in the study of them, encourage a slower, more deliberate way of thinking. It is a kind of work that rewards persistence and attention to detail, qualities that are sometimes overlooked in a world that moves quickly. And yet, through this careful process, we have learned that some stars are so large that their dimensions defy everyday intuition. We have measured objects whose atmospheres extend across distances comparable to the orbits of giant planets, whose outer layers drift into space in slow, steady winds, and whose lives are brief compared to smaller stars. All of this knowledge comes from light, faint streams of photons arriving at telescopes after journeys of unimaginable length. There is something comforting in that idea. The universe reveals its secrets not through sudden revelations, but through steady observation, careful measurement, and the quiet accumulation of understanding. If measuring the largest stars is so difficult, and if the largest stars are often unstable and constantly changing, can we ever be completely certain which star is truly the biggest? At first, the idea of the biggest star sounds like something that should be settled once and for all. It feels similar to measuring the height of a mountain or the length of a river. Once the measurement is made, the record stands and everyone agrees on the result. But astronomy does not work quite like that. When astronomers talk about the largest star, they usually do so with a quiet sense of caution, because the answer depends on measurements that are constantly improving, definitions that are not always perfectly sharp, and objects that are changing even as we observe them. So the title of biggest in astronomy is less like a permanent trophy, and more like a note written in pencil, subject to revision as new information arrives. One of the main reasons for this is distance. Measuring the size of a star requires knowing how far away it is, and distance is one of the hardest quantities to determine in astronomy. Even small uncertainties can lead to large changes in estimated size. Imagine a star whose brightness and temperature suggest a certain radius. If astronomers later discover that the star is actually 10% farther away than previously thought, the calculated size must increase as well. A change that seems modest in distance can lead to a much larger change in estimated radius. Over the years, improved measurements of stellar distances, especially from missions like Gaia, have refined the distances to many stars. In some cases, these new measurements have caused the estimated sizes of giant stars to shrink or grow significantly. This means that a star once listed as the largest known might later be replaced by another, not because the stars themselves changed, but because our measurements became more accurate. Another reason records change is that stars do not have solid surfaces. Unlike a planet or a moon, where there is a clear boundary between the object and space, a star's outer layers fade gradually into the surrounding environment. Astronomers usually define the radius of a star based on the photosphere, the layer where most visible light is emitted. But in giant stars, especially red supergiants and hypergiants, the atmosphere can be extended and irregular. The outer layers may be drifting outward, forming shells of gas and dust, or pulsating over time. Depending on how one defines the edge, the radius may vary. Different methods of observation, visible light, infrared, or radio wavelengths, can sometimes give slightly different answers because they probe different layers of the star's atmosphere. This means that the size of a giant star is not a single fixed number but often a range, reflecting the uncertainties in measurement and definition. There is also the issue of variability. Many of the largest stars are not stable in size. They pulsate, expanding and contracting over periods of months or years. Their brightness changes, their outer layers shift, and the exact location of the photosphere can move. If astronomers measure the star at one point in its cycle, they may obtain a slightly different radius than if they measure it at another time. Over long periods, these variations must be averaged, but short-term changes can still affect estimates. Another factor that complicates matters is dust. Giant stars often shed material that forms thick envelopes of gas and dust around them. This dust absorbs and scatters visible light, making the star appear dimmer and sometimes altering the apparent size of the emitting region. Infrared observations can penetrate this dust more effectively, but interpreting those observations requires careful modelling of how the dust interacts with the star's radiation. Small differences in those models can lead to different estimates of size. Then there is the matter of discovery itself. The universe is vast, and astronomers have not observed every star in the galaxy in detail. New surveys, especially those conducted in infrared wavelengths, continue to reveal previously unknown giant stars, some of which may rival or exceed the sizes of known contenders. It is entirely possible that even larger stars exist in regions of the galaxy that are heavily obscured by dust or simply too distant to have been studied carefully so far. So the list of the largest stars is always provisional, always open to revision as new observations are made. There is also a more subtle reason why records change, and it has to do with the models astronomers use to interpret their data. When scientists estimate the size of a distant star, they rely on theoretical models of stellar atmospheres, models that describe how temperature, pressure, and radiation behave in the outer layers of a star. These models are based on physics that has been tested in many contexts, but they still involve assumptions and approximations. As models improve, incorporating better physics and more detailed data, the estimated properties of stars can change. A star once thought to be larger may turn out to be somewhat smaller when analysed with a more accurate model, or vice versa. This is not a flaw in the scientific process. It is exactly how science is supposed to work. Knowledge advances through refinement, through the gradual reduction of uncertainty. Another interesting point is that different stars can be the largest in different ways. One star may have the greatest radius, another the greatest mass, another the highest luminosity. Depending on which property one emphasises, the title of biggest can refer to different objects. This is similar to how the tallest building, the heaviest ship, and the most populated city are all records of size, but they measure different things. In the case of stars, radius is usually the measure used when discussing the largest known stars, but even here uncertainties remain. There is also the question of time. Stars evolve. A star that is enormous today may shrink or explode in the future. Another star that is currently smaller may expand later in its life and briefly become larger than any star previously observed. So the title of largest star is not only uncertain in measurement but also temporary in time. Astronomers are essentially taking snapshots of stars at particular moments in their lives. The largest star today may not have been the largest a million years ago, and it may not be the largest a million years from now. This perspective adds an interesting dimension to the idea of records in astronomy. They are not permanent markers, but observations of a changing universe. There is something quietly fascinating about that. The universe is not static. It is dynamic, evolving, and full of processes that unfold over timescales far longer than human history. Even the largest stars, immense as they are only passing through particular stages of their lives, expanding, shedding material, and eventually ending in dramatic ways. Another reason records change is that astronomers sometimes discover that two stars previously thought to be separate objects are actually part of a binary or multiple system. In such cases, measurements of brightness and size must be reinterpreted, because the light observed from Earth comes from more than one star. This can lead to revisions in estimated luminosity and radius, sometimes significantly. There have also been cases where a star once thought to be a single enormous object turned out to be surrounded by a thick cloud of dust or gas that affected the measurements, leading to overestimates of its size. As observational techniques improve, these effects become clearer and the estimates become more reliable. All of this means that the ranking of the largest stars is not fixed. It shifts slowly as data improves and understanding deepens, and yet, despite these uncertainties, the general picture remains clear. There are stars so large that they dwarf our Sun by hundreds or even thousands of times in radius. There are stars whose atmospheres extend across distances comparable to the orbits of planets. There are stars whose outer layers are so diffuse that they blur into the surrounding space. Whether one particular star holds the record at any given time is less important than the fact that such stars exist at all. There is also a certain comfort in the way astronomy handles uncertainty. Instead of pretending to know more than it does, the field embraces error bars, ranges, and revisions. Measurements are reported with their uncertainties, and conclusions are stated cautiously. This careful approach allows knowledge to grow steadily, building on what came before without claiming finality too soon. And as we continue exploring the largest stars, it becomes natural to shift our attention from the measurements themselves to the star's inner workings. Because once we understand that some stars are truly enormous, another question arises almost automatically. What is happening inside such a star? What does the interior of a stellar giant look like? And how can something so vast remain stable, even for a short time? If you could somehow move closer to one of these immense stars, drifting inward through its outer layers, the first thing you would notice is how gradual everything feels. There would be no sharp boundary, no surface in the way we think of a planet's surface. Instead, the gas would slowly grow denser and brighter as you moved deeper, the light around you strengthening, the temperature rising little by little. A giant star is not hollow, and it is not uniform. Beneath those vast, glowing outer layers lies a structure that is surprisingly complex, a series of regions where different physical processes dominate, each layer playing a role in keeping the star shining. To understand what exists inside a giant star, it helps to begin at the center because that is where everything begins. At the core of a massive star, temperatures reach tens of millions of degrees, sometimes far higher. The pressure there is immense, created by the weight of all the layers above pressing inward under gravity. In that environment, atomic nuclei move so rapidly that they can overcome their natural repulsion and fuse together. Fusion is the engine of a star. It is the process that releases the energy which pushes outward against gravity, preventing the star from collapsing. In a star like the Sun, fusion in the core converts hydrogen into helium, and that process can continue steadily for billions of years. But in a giant star, especially one that has already expanded into a red supergiant or hypergiant, the situation is more complicated. The hydrogen in the core has often already been exhausted. The core contracts and heats up, and fusion begins to occur in shells surrounding the core rather than only at the very center. The core itself may be fusing heavier elements, helium into carbon, carbon into oxygen, and in the most massive stars, even heavier elements in a sequence that continues until iron is formed. This layered structure is sometimes compared to an onion, not because it looks like one in any literal sense, but because different layers of fusion occur at different depths. Near the center, heavier elements are fused, while farther out, lighter elements continue to burn in shells. Each layer produces energy, and that energy must travel outward through the star. How it travels depends on the conditions in each region. In some parts of a star, energy moves primarily through radiation, photons gradually making their way outward, being absorbed and re-emitted countless times. In other regions, especially in the outer layers of giant stars, energy is carried by convection, the slow rising and sinking of hot gas. Convection in giant stars is particularly dramatic. Instead of the small-scale boiling seen in a pot of water, or even the relatively modest convection cells of the Sun, giant stars can have convection cells so large that only a handful cover the entire surface. Imagine currents of gas rising and falling across distances greater than the orbit of Earth, moving slowly, steadily, over months or years. These currents shape the brightness of the star, causing subtle variations in light that astronomers can observe even from thousands of light years away. As energy moves outward, the temperature gradually decreases. By the time it reaches the outer layers, the gas has cooled to only a few thousand degrees, which is why these stars appear red or orange rather than white or blue. Yet even at those cooler temperatures, the environment would be utterly hostile by any human standard. The gas is still hot enough to glow, still moving in vast currents, still part of a system powered by nuclear reactions deep within. Another important feature of the interior of a giant star is pressure, and not just the pressure of gas. In massive stars, radiation pressure, the pressure exerted by light itself, plays a major role. Photons streaming outward from the core carry momentum, and when they interact with the gas in the star, they exert a force. In the most massive stars, this radiation pressure becomes so strong that it nearly balances gravity on its own. This delicate balance is one reason giant stars are often unstable. A small change in temperature or energy production can shift the equilibrium, causing the outer layers to expand or contract. These expansions and contractions are not always dramatic, but over time they can produce pulsations, gentle breathing motions of the star, where its radius increases and decreases slightly in a slow, rhythmic pattern. Some giant stars also experience more irregular variations, changes driven by the complex interplay of convection, radiation, and mass loss. Mass loss is another key part of the story inside a giant star. Although it may not be obvious from a distance, many giant stars are constantly shedding material. The outer layers are only loosely bound by gravity, and stellar winds carry gas outward into space. These winds can be slow compared to the violent explosions that end a star's life, but they are persistent. Over thousands or tens of thousands of years, they can remove a significant fraction of the star's mass. This lost material does not simply vanish. It drifts outward, forming shells or clouds of gas and dust that surround the star. Sometimes these clouds glow in infrared light, warmed by the radiation from the star itself. In a sense, a giant star is always surrounded by traces of its own past, layers of material it once contained, now slowly expanding into space. Deep inside, however, the most dramatic changes are taking place in the core. As heavier elements accumulate, the core becomes denser and hotter. Each stage of fusion produces less energy than the one before, and the timescales become shorter. Hydrogen burning may last millions of years, helium burning hundreds of thousands, carbon burning perhaps hundreds of years, and the final stages only days or hours. This accelerating sequence is like a clock ticking faster and faster, though from the outside the star may appear calm and steady. There is also an important difference between smaller stars and the largest ones. In a star like the Sun, the core is supported primarily by thermal pressure, the motion of hot particles, but in the most massive stars, other forms of pressure begin to play a role, including electron degeneracy pressure in certain stages of evolution. These forms of pressure arise from quantum mechanical effects, the rules that govern particles at very small scales. Even in an object as vast as a giant star, these microscopic principles can determine the star's ultimate fate. Another fascinating aspect of giant stars is the production of neutrinos. nearly massless particles that interact very weakly with matter. In the intense conditions of the core, enormous numbers of neutrinos are produced, and they escape almost immediately, carrying energy away. In the final stages of a massive star's life, neutrino emission becomes a major channel of energy loss, cooling the core and contributing to the collapse that eventually leads to a supernova. Yet all of this is hidden beneath the surface, invisible to ordinary observation. Astronomers cannot look directly into the core of a distant star. Instead, they infer what is happening inside by studying the light that emerges, by modelling stellar structure, and by comparing observations with theoretical predictions. It is a remarkable achievement, really, that by analysing faint points of light in the sky, scientists can reconstruct the internal processes of objects larger than entire planetary systems. There is also something quietly reassuring about the consistency of the physics involved. The same laws that govern the behaviour of gases, radiation and nuclear reactions on Earth apply inside these enormous stars. The scales are vastly different, but the principles are the same. Gravity pulls inward, pressure pushes outward, energy flows from hot regions to cooler ones, atoms fuse, releasing energy according to well-understood processes. These simple principles, repeated across unimaginable distances and times, give rise to the immense variety of stars we observe. Inside a giant star, everything is connected. The conditions in the core determine the energy output, which shapes the outer layers, which in turn influence how the star loses mass and evolves. It is a delicate balance, and it cannot last forever. Eventually, the core will reach a stage where fusion can no longer provide enough energy to support the star, and the final collapse will begin. But that part of the story lies ahead. For now, what matters is understanding that beneath the vast glowing surfaces of giant stars lies a complex and dynamic interior, a place where matter and energy are constantly in motion, where layers of fusion proceed in sequence, and where the forces of gravity and pressure remain locked in a long, patient struggle. And there is one more thought that often surprises people when they first consider the interiors of giant stars. Because these stars are so large, the journey of energy from the core to the surface can take an astonishing amount of time. Photons produced in the core may scatter and be reabsorbed countless times, taking thousands or even hundreds of thousands of years to reach the surface. So the light we see from a giant star today may have begun its journey deep inside the star long before human civilization existed in its present form. If it can take so long for energy to travel from the core to the surface, how long does it take light to cross the star itself? What does distance mean on the scale of a stellar giant? When we talk about the size of a giant star, it is easy to focus on the numbers, hundreds of times the radius of the Sun, sometimes more than 1,000. Comparisons to planetary orbits, to the distance between Earth and the Sun, to the paths of Jupiter or even Saturn. These comparisons help, but they still leave something out, because numbers and diagrams do not fully capture what distance really means on such a scale. One way to understand it more deeply is to think about light itself. Light is the fastest thing in the universe. It travels at about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in a single second. It moves so quickly that, in everyday life, it feels instantaneous. When you flip a switch, the room lights up immediately. When the sun rises, daylight seems to arrive all at once. But when distances grow large enough, even light begins to take noticeable time to travel. Here on Earth, light from the moon takes a little over a second to reach us. Light from the sun takes about 8 minutes. That means whenever you look at the sun, you're seeing it as it was 8 minutes ago. 8 minutes is not very long, so it usually doesn't feel significant. But now imagine distances far larger than the space between Earth and the Sun. In a giant star, especially one of the largest known, the distance from one side of the star to the other can be greater than the distance from the Sun to Jupiter. In some estimates, even greater than that. At that scale, light does not cross the star in seconds or minutes. It can take hours. Pause for a moment and let that idea settle in. A beam of light, travelling faster than anything else in the universe, needing hours just to cross a single star. It changes the way you think about size, not as a number, but as an experience of distance and time combined. If you could hover near the surface of such a star, the opposite edge would not be a nearby horizon. It would be unimaginably far away, far enough that the light leaving that region would not reach you until hours later. And yet, despite this vast scale, the star still behaves as a single object, held together by gravity, its internal processes linked across distances that would swallow entire planetary systems. There is another layer to this story, one that makes it even more fascinating. The light we see from a star's surface has already taken an incredibly long journey before it ever escapes into space. Deep inside a star, energy is produced in the core through nuclear fusion. Photons, particles of light, are created in enormous numbers, but those photons do not travel directly outward in straight lines. The interior of a star is so dense that photons are constantly absorbed and re-emitted, scattered in random directions. This process is sometimes described as a random walk. A photon may travel a tiny distance before being absorbed, then re-emitted in a new direction, only to be absorbed again. It repeats this process countless times, zigzagging slowly outward through the star's layers, although each individual step happens at the speed of light. The overall progress is extremely slow because of the constant scattering. For a star like the Sun, it may take tens of thousands, or even hundreds of thousands of years for energy produced in the core to reach the surface. In a giant star with its immense size and extended layers, the journey can be even longer in some regions. So the light that leaves the surface of a giant star today may have begun its journey long before human civilizations built their first cities. It has travelled not only across the vacuum of space but also through the dense interior of the star itself, a journey spanning vast distances and immense spans of time. This perspective changes the way we think about starlight. It is not just a flash of energy emitted in an instant. It is the final step in a very long process, the last stage of a journey that began deep in the star's core. And once that light escapes into space, its journey continues. For many giant stars, the light we see has travelled thousands of light years to reach Earth. A light year is the distance light travels in 1 year, about 9.46 trillion kilometres. Even that number is difficult to picture, but it helps to think of it as the distance light covers in a full year of continuous travel at the fastest possible speed. So when we observe a giant star thousands of light years away, we are seeing light that left the star thousands of years ago. That means we're always looking into the past. The star as it exists now in this very moment is slightly different from what we see, because its light has not yet reached us. There is something quietly calming about this idea. The night sky is not just a view of distant places, but a view of distant times. Each star is a message from the past carried by light across immense distances. Returning to the idea of size, the time it takes light to cross a giant star gives us a sense of the scale involved in its internal processes. Changes in one part of the star cannot instantly affect the entire structure. Information, carried by light or pressure waves, takes time to travel. In the outer layers of a red supergiant, convection currents move slowly, sometimes taking months or years to circulate. Shock waves from pulsations can take significant time to propagate through the atmosphere. Even the star's brightness variations can reflect processes unfolding across vast distances within the star. This means that a giant star is not a perfectly synchronized object. Different regions may be at slightly different stages of motion or temperature, contributing to the irregular variations astronomers observe. Another interesting consequence of size is the sheer scale of motion within these stars. Gas in the outer layers may drift outward at speeds of tens of kilometers per second, which sounds fast by everyday standards. But compared to the size of the star, these motions are gentle and slow. At such speeds, it can take months or years for material to move across a significant fraction of the star's radius. Processes that would seem rapid in a smaller environment become slow and gradual when stretched across such enormous distances. There is also a sense in which time itself feels different when thinking about objects on this scale. Human life unfolds over decades, civilizations rise and fall over centuries, but stars evolve over millions of years, and the largest stars pass through some of their most dramatic phases in times that, while short for a star, are still longer than recorded human history. Thinking about light travelling across a giant star or energy moving from its core to its surface invites a slower way of imagining change, one that unfolds gently rather than suddenly. And there is something peaceful about that perspective. The universe does not hurry. It moves at its own pace, guided by the steady laws of physics. Another way to grasp the meaning of stellar distance is to imagine what it would be like to travel across a giant star, not at the speed of light, but at speeds familiar to us. A commercial airplane travels at about 900 kilometers per hour. At that speed, circling Earth takes roughly 2 days. Crossing a giant star with a diameter larger than Jupiter's orbit would take years, even if you could somehow fly through its outer layers. Even a spacecraft travelling many times faster than an airplane would still require months or years to cross such a distance. These comparisons help bring the scale into more familiar terms, but they also reveal how limited our everyday experiences are when it comes to understanding cosmic distances. And yet, despite the immense scales involved, astronomers can measure these stars, estimate their sizes, and study their behaviour with remarkable precision. By analysing the light that reaches Earth, they can infer temperatures, motions, and compositions, reconstructing a picture of objects far beyond direct reach. It is a testament to the power of careful observation and patient reasoning. If a giant star can be larger than the orbit of Jupiter, what would happen if such a star replaced the Sun? How would the solar system change? What would the sky look like, and what would become of the planets we know so well? Let's imagine something together, slowly and without rushing, the way you might picture a scene before sleep, letting it form gently rather than forcing it into focus. Picture the solar system as it is now. The Sun sits at the centre, a steady sphere of light about 1.5 million kilometres across. Around it, the planets follow their familiar paths. Mercury closest, then Venus, then Earth, then Mars, and farther out the great gas giants, Jupiter and Saturn, moving in wide, unhurried orbits. This arrangement feels stable, almost permanent, because it has existed for billions of years. The distances are so vast and the motion so steady that change feels almost invisible on a human timescale. Now, imagine that the Sun is quietly replaced by a giant star, something like the immense stars we've been talking about, the kind sometimes described as a behemoth. Not suddenly, not explosively, just imagine that one day, in place of the Sun, there exists a red hypergiant whose outer layers extend far beyond the orbit of Mars, perhaps even beyond Jupiter. Take a moment to let that picture settle in your mind. The first thing to understand is that such a star would not look like the Sun. It would not be a bright compact disk in the sky. Its surface would be enormous, its light softer and redder, its outer layers stretched over a distance so vast that the inner solar system would lie deep within its atmosphere. Mercury and Venus would not orbit in empty space anymore. They would be immersed in the outer layers of the star itself, surrounded by hot, glowing gas. Earth, too, would be inside that enormous atmosphere, moving through regions of thin but intensely heated gas, the sky no longer black but filled with a dim, reddish glow. There would be no sunrise or sunset in the way we know them. The sky would not darken into night. Instead, it would remain softly luminous all the time, the light diffused through the star's vast atmosphere. But the light would feel different from sunlight. Red supergiants are cooler at the surface than the Sun, so their light is richer in red and infrared wavelengths. The warmth might feel less sharp, less intense in the blue and ultraviolet part of the spectrum, though the total energy in the environment would still be overwhelming for any planet like Earth. Of course, in reality, Earth could not survive such a change. The oceans would evaporate, the atmosphere would be stripped away or altered beyond recognition, and the surface would become uninhabitable long before the star reached its full expansion. But for the sake of this quiet thought experiment, imagine observing the scene from a safe distance, watching how the solar system would change. The most striking difference would be the sense of scale. From a position just outside the star's outer layers, the star would fill a huge portion of the sky. Its surface would not appear smooth. You would see enormous, slowly shifting regions of brighter and darker red, vast convection cells rising and falling over weeks or months. These currents would be larger than the orbit of Earth itself, immense rivers of hot gas circulating slowly, driven by the energy rising from deep within the star. Occasionally, you might see great arcs of gas lifting from the surface, drifting outward into space. These would be part of the star's stellar wind, material escaping the weak grip of gravity in the outer layers. Over time, these drifting clouds would form a glowing envelope around the star, illuminated from within, a slow and steady outflow rather than a sudden explosion. Jupiter and Saturn, depending on the exact size of the star, might still orbit outside the outer atmosphere, but their environments would be very different. The radiation from such a star would be intense, and the stellar wind much stronger than what our Sun produces. Their skies, if you could stand on their cloud tops, would be dominated by a vast red disk, far larger than the Sun appears from Earth today. Another interesting detail to consider is gravity. Even though the star would be enormously larger than the Sun, it would not necessarily have much greater mass. Many red supergiants have masses only 10 or 20 times that of the Sun, sometimes less. Gravity at a given distance depends on mass, not size, so the outer planets might continue orbiting in roughly similar paths, though affected by mass loss from the star and the drag of the stellar wind. The inner planets, however, would not remain intact. Immersed in the star's atmosphere, they would gradually lose energy and spiral inward, their surfaces heated and eroded, eventually dissolving into the star itself. It is a slow process in astronomical terms, but inevitable. There is also the matter of time. A star in this giant phase does not remain that way for long. Compared to the billions of years the Sun spends on the main sequence, the red supergiant stage lasts only a few 100,000 years, sometimes less. So even in this imagined scenario, the behemoth at the centre of the solar system would be living in a brief chapter of its life, already approaching the final stages of its evolution. From a safe vantage point far away, you might watch as the star slowly changed over centuries and millennia. Its brightness might vary slightly. Its outer layers might expand or contract. Great shells of gas might drift outward, forming faint glowing clouds around it. And eventually deep in the core, processes would begin that lead toward a supernova, though that part of the story unfolds far beyond the calm timescale of our thought experiment. There is another aspect of this scenario that is worth considering, something quieter but just as fascinating. Think about how the sky would appear from a distant point in the outer solar system, perhaps near the orbit of Neptune. The behemoth at the centre would appear enormous, but not dazzlingly bright in the way a smaller, hotter star might be. Its light would be deep red, and much of its energy would be in infrared wavelengths invisible to the human eye. The surrounding space might glow faintly with scattered light from the clouds of dust and gas the star had shed. It would be a different kind of brightness, softer, more diffuse, less sharply defined. This difference in appearance reminds us that size and brightness are not the same thing. A star can be vast yet relatively cool at the surface, spreading its energy over such a large area that its light feels gentle compared to smaller, hotter stars. Another thing that becomes clear in this thought experiment is how delicate planetary systems really are. The stability of our solar system depends on the steady output and moderate size of the Sun. A change in the Sun's size or luminosity on the scale of a red supergiant would transform everything. In fact, our own Sun will one day expand into a red giant, though not nearly as large as the most extreme stars. In about 5 billion years, it will grow large enough to engulf Mercury and Venus, and possibly Earth as well. So in a sense, this thought experiment is not entirely imaginary. It is a glimpse, in a much more extreme form, of a process that will eventually happen in our own solar system, though far in the future. There is something strangely calming about thinking on these timescales. The changes are immense, but they unfold so slowly that there is no urgency, no suddenness, just the steady progression of stellar evolution. Another perspective worth considering is how such a star would influence the surrounding interstellar space. The stellar wind from a giant star can carry vast amounts of material outward, enriching the surrounding region with heavier elements. Over time, this material mixes with interstellar clouds, becoming part of the raw material for new stars and planets. In this way, even the death of a giant star contributes to the birth of future worlds. So if a behemoth replaced the Sun, the solar system would not simply be destroyed. Its material would be recycled, gradually dispersed and eventually incorporated into new systems elsewhere in the galaxy. This cycle of creation and transformation is one of the most fundamental patterns in the universe. As you picture this immense star at the centre of the solar system, it is worth noticing how the scale changes your sense of distance and motion. Orbits that once seemed vast become small. Distances that once felt enormous are swallowed by the star's outer layers. It is a reminder that scale is always relative. What feels large in one context can feel small in another, and perhaps that is part of why giant stars capture the imagination so strongly. They stretch our sense of proportion, encouraging us to think beyond the limits of everyday experience. Yet even these giants are not eternal. Their immense size is temporary, a stage in a life that burns quickly and ends dramatically. Why do the largest stars live such short lives? What is it about being enormous that causes a star to burn so quickly and fade so soon, at least by cosmic standards? At first, it might seem natural to assume that a larger star would live longer. After all, a bigger object contains more material, and more material might suggest more fuel to burn. In everyday life, that logic often holds true. A larger tank of fuel lasts longer than a smaller one. A larger candle can burn longer than a thin one. But stars do not follow that simple rule, and in fact, the opposite is true. The largest stars in the universe live the shortest lives. To understand why, it helps to begin with the basic engine of a star, the process of nuclear fusion. Deep in the core, hydrogen atoms fuse into helium, releasing energy. That energy produces pressure that pushes outward, balancing the inward pull of gravity. As long as this balance is maintained, the star remains stable. Now consider what happens when a star is very massive. A more massive star has stronger gravity pulling inward. To counteract that gravity, the core must produce more energy. And to produce more energy, fusion must occur at a much faster rate. This is the key point. Larger stars do have more fuel, but they burn that fuel far more quickly. The difference is dramatic. A star twice the mass of the Sun does not simply burn fuel twice as fast, it may burn several times faster. A star 10 times the mass of the Sun can burn tens of thousands of times more brightly. The relationship between mass and energy output is not linear. It accelerates rapidly as mass increases. It is a bit like comparing a small campfire to a roaring furnace. The furnace consumes fuel at a much greater rate, even though it contains more fuel to begin with. Because of this, massive stars race through their main sequence phase, the period when they are steadily fusing hydrogen in their cores. While the Sun will spend about 10 billion years in this stage, a star with 20 times the Sun's mass might remain on the main sequence for only a few million years. In cosmic terms, that is an extraordinarily short life. After the hydrogen in the core is exhausted, the star begins to evolve. The core contracts, heats up, and new types of fusion begin. Helium fuses into carbon and oxygen. In even more massive stars, fusion continues, producing heavier and heavier elements in successive stages. Each stage occurs more quickly than the last. Hydrogen burning may last millions of years. Helium burning may last hundreds of thousands. Carbon burning might last only a few hundred years. Later stages can last days or even hours. It is as if the star is accelerating toward its end, burning through its remaining fuel in increasingly rapid bursts. There is another factor that shortens the lives of massive stars, and that is mass loss. The largest stars lose enormous amounts of material through stellar winds. Radiation pressure pushes gas outward, and the outer layers, already loosely bound by gravity, drift away into space. Over time, a massive star can lose a significant fraction of its mass in this way. This loss of mass changes the structure of the star and can alter its evolution. In some cases, the star sheds so much material that it transitions into a different type of star before reaching the final stages of its life. Mass loss also enriches the surrounding interstellar medium with heavier elements, contributing to the cycle of star formation that continues throughout the galaxy. Another reason massive stars live short lives is that their cores are hotter and denser than those of smaller stars. Higher temperatures mean faster nuclear reactions. The rate of fusion increases dramatically with temperature, so even a small increase in core temperature can lead to a large increase in energy production. This creates a kind of feedback loop. Strong gravity compresses the core, raising the temperature. Higher temperature increases the fusion rate. Faster fusion produces more energy, which supports the star against gravity but also accelerates the consumption of fuel. The star shines brilliantly, but at the cost of a shortened lifetime. There is also the role of radiation pressure to consider. In the most massive stars, radiation pressure becomes a significant part of the force balance in gravity. Photons streaming outward exert pressure on the gas, helping to support the star's outer layers. But this balance is delicate. Small changes in temperature or energy production can cause the outer layers to expand or contract. This contributes to the instability of hypergiants and other massive stars, making their lives more turbulent and unpredictable. Another interesting detail is that massive stars do not mix their fuel as efficiently as smaller stars in some stages of their evolution. While convection can transport material in certain regions, other regions remain stratified, with heavier elements sinking toward the core and lighter elements remaining in outer layers. This layered structure means that not all of the star's hydrogen is available for fusion at once. Only the hydrogen in the core participates in the main sequence phase, and once that core hydrogen is exhausted, the star must change its structure to continue producing energy. This further limits the effective fuel supply available at any given time. Despite their short lives, massive stars have an enormous impact on their surroundings. Their intense radiation ionizes nearby gas, creating glowing nebulae. Their stellar winds carve bubbles in the interstellar medium, and when they finally explode as supernovae, they scatter heavy elements across vast regions of space. These elements, carbon, oxygen, silicon, iron, and many others, become part of new stars, planets, and eventually living organisms. In this sense, the brief, brilliant lives of massive stars play a crucial role in the evolution of the galaxy. There is also something quietly striking about the contrast between size and lifespan. A giant star may be hundreds or thousands of times larger than the Sun, yet it lives only a tiny fraction as long. It is a reminder that scale does not always correspond to duration. In many natural processes, intensity shortens life rather than prolonging it. If you were to observe a massive star over its lifetime, the changes would still appear slow by human standards. Even a few million years is an immense span of time compared to the length of human history. But compared to the billions of years that smaller stars can endure, it is brief. Astronomers sometimes describe massive stars as living fast and dying young, though of course this is only a metaphor. Stars do not experience time or make choices. They simply follow the laws of physics, their evolution determined by mass, composition, and the processes occurring in their cores. Still, the metaphor captures something true about the contrast between brilliance and longevity. Another aspect of massive stars that contributes to their short lives is their internal structure during the later stages of evolution. As heavier elements accumulate in the core, fusion becomes less efficient at producing energy. Each successive stage releases less energy per reaction, and the core must contract further to reach the temperatures needed for fusion. Eventually, the core reaches a stage where fusion can no longer provide enough energy to support the star. Iron, the final product of fusion in massive stars, does not release energy when fused. Instead, it absorbs energy, making further fusion impossible. When the core becomes mostly iron, the balance between gravity and pressure can no longer be maintained. Collapse begins, leading to one of the most dramatic events in the universe, a supernova explosion. But that part of the story unfolds in the next stage of stellar evolution. For now, it is enough to understand that the larger stars burn their fuel rapidly, lose mass through powerful winds, and pass through their evolutionary stages at a much faster pace than smaller stars. Their immense size is not a sign of stability or permanence. It is a phase, a brief period in a life that is both brilliant and short by cosmic standards. Long before a giant star reaches the moment of its final collapse, the ending has already begun, quietly and gradually deep within the core. From the outside, the star may still appear steady, glowing with its familiar reddish light, its outer layers drifting slowly outward in gentle stellar winds. Nothing about its appearance suggests urgency. Nothing hints at how close it may be, in cosmic terms, to the end of its life. But inside, the balance that has sustained the star for millions of years is changing. To understand how giant stars end, it helps to return once more to the core, because that is where the story always turns. A massive star does not burn one type of fuel for its entire life. Instead, it moves through stages, fusing different elements in sequence as the core grows hotter and denser. Hydrogen is fused into helium, then helium into carbon and oxygen. In the most massive stars, fusion continues, producing neon, magnesium, silicon, and eventually iron. Each stage of fusion happens more quickly than the one before. Hydrogen burning may last millions of years, but the later stages become astonishingly brief. Silicon burning, the final stage before collapse, can last only a matter of days. This accelerating pace is one of the reasons astronomers sometimes describe the late life of a massive star as a kind of countdown, though it is not a countdown anyone could observe in real time. The processes unfold far too slowly for a human observer to notice directly, yet far too quickly, in stellar terms, for the star to remain stable for long. The reason iron marks the turning point lies in the nature of nuclear fusion itself. Fusion releases energy only when lighter elements combine to form heavier ones up to iron. Beyond iron, fusion requires energy instead of releasing it. When the core becomes rich in iron, the star loses its ability to generate energy through fusion at the center. The outward pressure that has balanced gravity for so long begins to weaken. At first, the change is subtle. The core contracts slightly, heating further, but no new source of energy appears to halt the contraction. Gravity begins to take over. This is the beginning of the slow approach to catastrophe. The outer layers of the star remain largely unaffected at this stage. Light continues to shine. Stellar winds continue to carry material outward. From a distance, nothing seems dramatically different, but the core, hidden beneath layers of gas, is becoming denser and denser. Electrons are forced closer together, and the pressure inside rises to extraordinary levels. Eventually, a point is reached where the core can no longer support itself. Collapse becomes inevitable, and when that collapse begins, it happens with astonishing speed. The core, which may be as large as Earth, can collapse in a fraction of a second. Gravity pulls matter inwards so rapidly that atoms are crushed together, protons and electrons combining to form neutrons. The core becomes an incredibly dense object, a neutron star in many cases, or a black hole if the mass is great enough. This sudden collapse sends a shock wave outward through the star. The shock, combined with a flood of neutrinos released during the collapse, blows the outer layers of the star into space in a supernova explosion. For a brief time, the star can outshine an entire galaxy, releasing more energy in a few weeks than the Sun will emit in its entire lifetime. But what makes this ending remarkable is not only the explosion itself, but the long, quiet build-up that precedes it. For hundreds of thousands of years, the star may exist in a state of growing instability, its outer layers pulsating, its mass slowly decreasing through stellar winds, its core moving steadily toward the point where fusion can no longer sustain it. In some giant stars, this late stage is marked by episodes of increased mass loss. The star may shed large amounts of material, forming expanding shells of gas that glow faintly in the surrounding space. These shells can sometimes be observed long before the final explosion, providing clues about the star's internal state. Astronomers studying stars like Betelgeuse, for example, have observed evidence of past eruptions, layers of gas drifting outward, each one a record of changes deep within the star. These events are not violent on the scale of a supernova, but they are signs that the star is entering its final phases. Another aspect of this slow approach to catastrophe is the change in the star's internal structure. As heavier elements accumulate in the core, the layers of fusion become more complex. Different shells of burning material surround the core, each producing energy at a different rate. This layered structure can become unstable, leading to fluctuations in brightness and changes in the star's atmosphere. From Earth, these changes may appear as variations in light over months or years, subtle shifts that astronomers carefully monitor. There is something quietly fascinating about observing a star that is nearing the end of its life. The light we see left the star years or even centuries ago. Yet within that light are clues about processes unfolding deep inside, processes that will eventually lead to one of the most powerful events in the universe. It is a reminder that even the most immense and seemingly eternal objects are subject to change. There is also a broader perspective to consider. When a giant star explodes, it does not simply vanish. The material it ejects spreads into space, forming expanding clouds of gas enriched with heavy elements. These elements, forged in the core and during the explosion itself, become part of the interstellar medium. Over time, they may be incorporated into new stars, planets, and perhaps even living organisms. In this way, the death of a giant star is also a beginning. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were formed in the interiors of stars and scattered into space by events like supernovae. The slow approach to catastrophe in a giant star is part of a cycle that ultimately leads to the formation of new worlds. Yet from the star's own perspective, if one could speak of such a thing, the ending is inevitable. Gravity always waits, patient and persistent, and when fusion can no longer provide the outward pressure needed to resist it, collapse follows. One of the most striking aspects of this process is how quickly the final moment arrives after such a long build-up. A star may spend millions of years evolving, shedding mass, and gradually changing its internal structure, but the final collapse and explosion occur in a matter of seconds and hours. It is like a long, quiet evening followed by a sudden flash of lightning, brief but brilliant. Astronomers continue to study the late stages of massive stars in great detail, searching for signs that might indicate how close a particular star is to exploding. Changes in brightness, shifts in spectral lines, and observations of surrounding gas all provide clues, but predicting the exact timing of a supernova remains extremely difficult. Stars do not announce their endings in advance. Still, by observing many stars at different stages of evolution, scientists can piece together a general picture of how these endings unfold. What happens after the explosion itself? How do supernovae shape the galaxy? And what remains after the outer layers have been blown away? When the end finally arrives for a giant star, it does not happen quietly. For millions of years, the star has burned, expanded, and shed material in slow, steady processes that unfold almost too gradually to imagine. But the final act is different. The collapse of the core and the explosion that follows release an extraordinary amount of energy in a very short time, and for a brief period the dying star can outshine nearly everything else in its host galaxy. This event is what we call a supernova. From a great distance, a supernova appears first as a sudden brightening, a point of light that was once ordinary becoming intensely luminous over a matter of days. Ancient observers sometimes recorded these events as new stars, appearing where none had been visible before. In reality, the star had been there all along, but the explosion made it dramatically brighter for a short time. Modern astronomy has revealed what is happening behind that sudden brilliance. When the core of a massive star collapses, gravity compresses matter to incredible densities. The outer layers, which had been held up by the pressure from fusion in the core, suddenly lose their support. They fall inward briefly, then rebound outward in a shock wave that tears the star apart. The energy involved is difficult to put into familiar terms. In just a few seconds, the collapsing core releases more energy than the Sun will produce in its entire lifetime. Most of that energy escapes in the form of neutrinos, nearly invisible particles that pass through matter almost without interacting. A smaller fraction drives the explosion we see, sending the star's outer layers racing outward into space. For weeks or months, the expanding debris glows intensely, heated by radioactive elements created in the explosion. Gradually the brightness fades, and what remains is a vast expanding cloud of gas called a supernova remnant. These remnants can persist for thousands of years, slowly spreading into the surrounding interstellar medium. Observations of remnants such as the Crab Nebula show intricate filaments of glowing gas, moving outward at thousands of kilometers per second, carrying with them the elements forged in the heart of the star. This is one of the most important roles giant stars play in the galaxy. During their lives, they fuse lighter elements into heavier ones. During their deaths, they scatter those elements across space. Without supernovae, the universe would be very different. The early universe contained mostly hydrogen and helium, with only trace amounts of heavier elements. The carbon, oxygen, silicon, iron, and many other elements that make up planets and living organisms were created inside stars and dispersed by stellar explosions. Every atom of calcium in your bones, every atom of iron in your blood, was once part of a star that lived and died long before the Sun formed. Thinking about this can change the way we see supernovae. They are not only endings, they are also beginnings, the process by which the raw material for new stars and planets is distributed through the galaxy. When the expanding gas from a supernova mixes with nearby clouds, it can trigger the formation of new stars. The shock waves compress regions of gas, causing them to collapse under their own gravity. In this way, the death of one star can help give birth to many others. This cycle has been repeating for billions of years. Stars form, shine, and explode. Their remnants enrich the interstellar medium, and new stars form from that enriched material. Over time, the chemical complexity of the galaxy increases, making possible the formation of rocky planets and, eventually, life. But the influence of supernovae goes beyond the creation of elements and the triggering of star formation. The energy released in these explosions shapes the structure of entire regions of the galaxy. When a supernova occurs, the expanding shock wave sweeps up surrounding gas, creating vast bubbles in the interstellar medium. Multiple supernovae occurring in the same region, such as in a cluster of massive stars, can combine to form enormous cavities filled with hot, tenuous gas. These structures, sometimes called superbubbles, can span hundreds of light years. They affect how gas moves through the galaxy, how new stars form, and how energy is distributed across large scales. In this way, Giant stars act as engines of change, not only during their lives but also in their deaths. There is another possible outcome for the core of a massive star after a supernova. If the remaining core is not too massive, it becomes a neutron star, an object of extraordinary density. A neutron star can contain more mass than the Sun compressed into a sphere only about 20 kilometers across. The gravity on the surface of such an object is so strong that a single teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars spin rapidly, emitting beams of radiation that sweep through space like the beam of a lighthouse. When these beams cross Earth, we observe them as pulsars, regular flashes of radio waves or other radiation. If the core is even more massive, gravity overwhelms all other forces and the core collapses into a black hole. In that case, the gravitational field becomes so strong that not even light can escape. Black holes formed from massive stars are among the most fascinating objects in the universe, and their formation marks the final stage in the life of the most massive giants. Sometimes, under the most extreme conditions, the explosion itself can take an unusual form. Certain very massive stars may undergo what is called a pair instability supernova, a process so energetic that it completely disrupts the star, leaving no remnant behind. In such an event, the entire star is blown apart, and nothing remains but the expanding cloud of debris. These events are rare, but they demonstrate just how powerful the deaths of giant stars can be. There is also the matter of timing. Giant stars live short lives, but even so, supernovae are relatively rare events in any single galaxy. In the Milky Way, a supernova is expected to occur roughly once every century or so, though many go unnoticed because they are obscured by dust or occur on the far side of the galaxy. Occasionally a supernova becomes visible to the naked eye, as happened in 1054 when a star in the constellation Taurus exploded, creating the Crab Nebula. Historical records from Chinese and Middle Eastern astronomers describe a bright new star visible even during the day for weeks. Such events remind us that the galaxy is not static. It is alive with processes unfolding over timescales both long and short. Another interesting aspect of supernovae is how they affect nearby planetary systems. A supernova occurring close enough to a planet could have significant effects on its atmosphere and environment. Fortunately, there are no massive stars close enough to Earth to pose such a threat in the foreseeable future. Most giant stars are located thousands of light years away, far enough that their explosions are spectacular to observe but harmless to us. And yet the influence of ancient supernovae can still be detected. Scientists have found traces of radioactive isotopes in ocean sediments that may have been deposited by supernovae occurring millions of years ago, relatively close in astronomical terms, but still far enough away to avoid causing major damage to life on Earth. This evidence provides a reminder that the processes shaping the galaxy are not entirely distant from our own history. As we consider the lives and deaths of giant stars, there is something quietly profound about their role in the universe. They are short-lived but immensely influential. They burn brightly, expand to enormous sizes, and end in explosions that reshape their surroundings and seed the galaxy with new elements. Their lives are brief compared to smaller stars, but their impact is lasting. And yet, even these extraordinary stars do not grow without limit. There are boundaries set by physics, limits on how massive or how large a star can become before instability and mass loss prevent further growth. After hearing about stars so large that they could swallow the orbits of planets, it is almost impossible not to wonder whether the universe might hold even greater extremes. If some stars already stretch to sizes that challenge imagination, could there be others still larger, hidden somewhere in the galaxy or beyond? Could there be stars so vast that even the giants we have discussed would seem modest by comparison? It is a natural question, and one that astronomers have asked for a long time. The answer, like many things in astronomy, is both yes and no. Yes, it is possible that stars slightly larger than the current record holders exist, or will be discovered in the future. But no, There are real physical limits that prevent stars from growing without bound. Nature, it turns out, sets boundaries, even in the vastness of space. To understand those limits, it helps to begin with the process of star formation. A star is born when gravity pulls together a cloud of gas and dust. The more material that gathers, the more massive the star can become. At first, it might seem that as long as enough gas is available, a star could simply keep growing. But something important happens as a forming star becomes more massive. Its brightness increases dramatically. The energy pouring out from its surface produces radiation pressure, a force exerted by light itself. This pressure pushes outward on the surrounding gas, opposing the inward pull of gravity. At a certain point, the radiation becomes strong enough to blow away the very material that is trying to fall into the star. In effect, the star begins to shut off its own supply of fuel before it can grow too large. This process places a natural limit on how massive a star can become during its formation. Observations suggest that stars rarely exceed about 150 to 200 times the mass of the Sun. There may be rare exceptions under unusual conditions, but beyond this range, forming a stable star becomes extremely difficult. Mass, however, is not the same as size. Some of the largest stars in terms of radius are not the most massive. They are stars that have expanded late in their lives, their outer layers swelling outward to enormous distances. So the question of the largest star is really about how far a star's atmosphere can expand while still remaining bound by gravity. Here again, there are limits. As a star expands, its outer layers become more weakly bound. Gravity decreases with distance from the centre, and the gas in the outer atmosphere becomes increasingly tenuous. Stellar winds carry material away, and pulsations can lift large amounts of gas into space. If a star expands too far, its outer layers may simply drift away faster than gravity can hold them. The star cannot maintain an arbitrarily large radius, because the material at the edge would no longer remain part of the star for long. This balance between expansion and mass loss sets an upper boundary on how large a star can appear. Another factor that limits size is temperature. A star's radius is related to its luminosity and surface temperature. For a star to become extremely large, its surface must be relatively cool, allowing its energy to be spread over a vast area. But if the surface becomes too cool, the star's outer layers may become unstable, forming dust and molecules that enhance mass loss even further. This process can accelerate the shedding of material, effectively preventing the star from growing larger. There is also the matter of internal structure. The energy produced in the core must travel outward through the star. If the outer layers become too extended, convection and radiation may no longer transport energy efficiently enough to maintain stability. Instabilities can develop, leading to pulsations or eruptions that carry material away. All of these effects work together to set a practical limit on how large a star can become. That said, the universe often finds ways to surprise us. Astronomers continue to discover new giant stars, some of which challenge previous expectations. Improved infrared surveys have revealed stars hidden behind thick clouds of dust, and better distance measurements have revised the estimated sizes of known stars. So while there may be limits, the exact location of those limits is still an area of active research. Another interesting possibility involves stellar mergers. In dense star clusters, close encounters between stars can occur. In some cases, two massive stars may collide and merge, forming a single larger star. Such merger products can be unusually massive and luminous, at least for a time. These merged stars may briefly exceed the typical limits for single star formation, though they are often unstable and lose mass rapidly. Even so, they provide a glimpse of how nature can occasionally push beyond the usual boundaries. There is also the question of stars in the early universe. The first generation of stars, known as Population 3 stars, formed from primordial gas containing almost no heavy elements. The absence of heavier elements may have allowed some of these stars to grow much more massive than stars forming today, perhaps hundreds of times the mass of the Sun or more. These ancient stars are long gone now, having lived short lives and exploded billions of years ago. But their existence suggests that under different conditions, the universe may have produced stars even more extreme than those we see today. Still, even these primordial giants would have faced limits. Gravity, radiation pressure, and mass loss remain fundamental forces that cannot be ignored. Another way to think about the limits of stellar size is to consider the concept of stability. A star is a balance between inward and outward forces. If that balance is pushed too far in either direction, the star changes. It may contract, expand, shed material, or collapse entirely. The largest stars we observe are already near the edge of stability. Their outer layers are turbulent, their brightness varies, and their mass loss rates are high. They are, in a sense, living on borrowed time, existing in a state that cannot last long. So while it is possible that slightly larger stars than the current record holders exist, there is no evidence for stars vastly larger than those already known. The limits imposed by physics seem to prevent stars from growing indefinitely. There is something quietly reassuring about this idea. Even in a universe of immense scale, there are boundaries, rules that shape what can and cannot exist. At the same time, those boundaries are far beyond anything we encounter in everyday life. The largest stars are still so enormous that their limits remind us not of restriction, but of how vast the possible range of nature truly is. It is also worth remembering that the title of largest star is always provisional. New observations may refine our understanding, and new discoveries may reveal stars that challenge previous records. The universe is vast, and there is always more to learn. Yet the deeper lesson is not about which particular star holds the record. It is about the processes that allow stars to grow, expand, and evolve, and the forces that ultimately set the limits of those processes. Long before a giant star reaches the end of its life, it is already changing the space around it in quiet but powerful ways. It is easy to imagine stars as isolated points of light, distant and separate, each one shining in its own place without affecting anything beyond its own surface. But the largest stars do not behave like that. Their influence extends far beyond their visible edges, reaching into the surrounding gas and dust, reshaping entire regions of space over time. One of the first ways a massive star affects its environment is through light itself. Giant stars are incredibly luminous. Even when their surfaces are relatively cool compared to smaller, hotter stars, their enormous size means they emit vast amounts of energy. That radiation travels outward in all directions, striking nearby clouds of gas. When high-energy light from a massive star encounters hydrogen gas, it can strip electrons from atoms, a process called ionization. Ionized hydrogen glows faintly, producing the soft reddish light seen in many nebulae. Entire regions of space can be lit up in this way, creating vast glowing clouds visible across thousands of light years. These glowing regions, known as H2 regions, are often found around clusters of massive stars. The stars illuminate and heat the surrounding gas, creating enormous bubbles of ionized material. Over time, this radiation does more than simply make the gas glow. It heats the gas, increasing its pressure and causing it to expand outward. The expanding gas pushes against the surrounding material, carving cavities in the interstellar medium. These cavities can grow to enormous sizes, sometimes hundreds of light years across. From a distance, they appear as hollowed-out regions surrounded by dense shells of gas and dust, shaped by the combined radiation and stellar winds of many massive stars. Stellar winds are another powerful way giant stars shape their surroundings. Even during relatively calm phases of their lives, massive stars lose material in steady outflows of gas. These winds can travel at hundreds or even thousands of kilometers per second, carrying mass and energy into the surrounding space. When these winds collide with the interstellar medium, they create shock waves that compress and heat the gas. Over time, this process forms expanding bubbles of hot, thin plasma surrounded by cooler, denser shells. In regions where many massive stars form together, their winds combine, producing enormous structures called superbubbles. These can span large portions of a galaxy's spiral arms, influencing how gas moves and how new stars form. There is an interesting balance at work here. On one hand, the radiation and winds from giant stars can disrupt star formation by dispersing gas clouds. On the other hand, the shockwaves created by these processes can compress parts of those clouds, triggering the collapse of dense regions and the birth of new stars. So the larger stars both inhibit and encourage star formation, depending on the conditions. They are both creators and destroyers, shaping the cycle of stellar birth and death in complex ways. Another important contribution of giant stars comes from the elements they produce. Inside their cores, nuclear fusion creates heavier elements from lighter ones. When these stars lose mass through winds or explode as supernovae, those elements are released into space. This enrichment of the interstellar medium is crucial. The first generation of stars in the universe formed from almost pure hydrogen and helium. Over billions of years, successive generations of stars have added heavier elements to the cosmic environment. Today, the gas clouds that form new stars contain a rich mixture of elements, including carbon, oxygen, silicon, and iron. These elements allow planets to form, create complex chemistry, and ultimately make life possible. In this sense, giant stars are not only shaping their immediate surroundings, but also contributing to the long-term evolution of galaxies. There is also the influence of motion. Massive stars often form in clusters, and their interactions can affect the dynamics of those clusters. When a giant star explodes as a supernova, the sudden loss of mass can alter the gravitational balance of the cluster, sending nearby stars into new orbits, or even ejecting them into interstellar space. The shock waves from supernovae can travel for tens or hundreds of light years, sweeping up gas and dust as they move. These expanding shells of material may eventually slow and merge with the surrounding medium, but not before leaving their mark on the structure of the galaxy. Astronomers studying the Milky Way have identified enormous structures, vast arcs and bubbles of gas, that are thought to be the combined remnants of multiple supernovae and stellar winds from massive stars over millions of years. These structures are not immediately visible to the naked eye, but radio and infrared observations reveal their presence, showing that the galaxy is full of cavities and filaments shaped by the lives and deaths of giant stars. Another way the larger stars shape the universe is through their influence on cosmic rays. Supernova explosions accelerate particles to extremely high energies, sending them racing through space at nearly the speed of light. These cosmic rays travel across the galaxy, occasionally interacting with planetary atmospheres and magnetic fields. While most cosmic rays pose little threat to life on Earth thanks to our planet's protective magnetic field and atmosphere, they play an important role in the chemistry of interstellar clouds, influencing the formation of molecules and the ionization of gas. In this way, the effects of giant stars extend even into processes that are not immediately visible. There is also a deeper perspective to consider. When we look at a galaxy from a distance, we see not just individual stars but patterns, spiral arms, clusters, and glowing nebulae. Many of these large-scale features are shaped by the energy released by massive stars. The spiral arms of galaxies are regions where star formation is active, and massive stars are among the brightest objects in those regions. Their light illuminates the gas, their winds shape the clouds, and their supernova inject energy into the surrounding medium. Without giant stars, galaxies would look very different. They would be dimmer, less structured, and chemically simpler. There is something quietly remarkable about the fact that a relatively small number of very large stars can have such a profound influence on an entire galaxy. Most stars are small and long-lived, like red dwarfs, but it is the rare giants, burning brightly and briefly, that drive much of the visible drama in the cosmos. Another aspect of this influence is time. The effects of a giant star's life and death can persist long after the star itself is gone. Supernova remnants can remain visible for thousands of years, The elements dispersed by stellar winds and explosions may become part of new stars millions of years later. In this sense, giant stars leave a legacy that continues long after their own light has faded. There is also a connection between these processes and our own existence. The atoms that make up Earth and everything on it were forged in earlier generations of stars. Without the cycles of stellar birth and death, the universe would contain only the simplest elements, and the complex chemistry needed for life would not exist. So when we look at giant stars, we are not just looking at distant objects, we are looking at part of the history that made our own world possible. And yet, despite their immense power and influence, giant stars are only one part of a much larger story. The universe contains galaxies, clusters of galaxies, and structures on scales far beyond even the largest stars. Thinking about these scales can lead to a different kind of reflection, one that turns inward as much as outward. Why do humans find such fascination in extremes, in the largest stars, the biggest black holes, the most distant galaxies? What is it about these immense objects that captures our imagination so strongly? It's interesting to notice how often our attention is pulled toward the largest, the brightest, or the most extreme things we can find. This is true not only in astronomy, but in many parts of life. People are curious about the tallest mountains, the deepest oceans, the fastest animals, the most distant galaxies. There is something about extremes that naturally captures the human mind. When it comes to stars, this curiosity becomes especially strong. The idea that there are stars so large they could swallow the orbits of planets feels almost unbelievable at first. And yet, once we hear about them, it becomes difficult not to wonder just how large they can be, how they form, and what ultimately happens to them. Part of this fascination comes from contrast. Human beings evolved in an environment where the largest objects we encountered were mountains, forests, and oceans. Even the largest structures we build today, cities, bridges, or ships, are tiny compared to the scales found in astronomy. When we learn about stars thousands of times larger than the Sun, or distances measured in light years, it stretches our sense of scale far beyond anything our senses were designed to handle. That stretching of perspective is both challenging and calming at the same time. Challenging because it reminds us how small we are compared to the universe. Calming because it places many everyday worries into a wider context. The problems that seem large during the day can feel smaller when seen against the backdrop of a galaxy filled with stars. There is also a deep sense of curiosity built into the human mind. From early childhood, people ask questions about how things work and what lies beyond the horizon. This curiosity likely played an important role in human survival, encouraging exploration, problem-solving, and learning. Looking up at the night sky is one of the oldest forms of exploration. Long before telescopes existed, people noticed patterns among the stars, tracked the movements of planets, and wondered about the nature of the lights overhead. Stories and myths were created to explain what could not yet be measured. Today, science provides different kinds of answers, but the sense of wonder remains much the same. Another reason cosmic extremes attract attention is that they are relatively easy to describe in simple terms. Saying that a star is 1,000 times larger than the Sun is a statement that anyone can understand, even without detailed knowledge of astrophysics. The numbers themselves carry a sense of drama. Yet behind those numbers are complex processes: nuclear fusion, radiation pressure, convection, and stellar winds, all governed by physical laws that operate quietly and consistently. There is something satisfying about knowing that even the most extreme objects in the universe follow the same basic rules as everything else. Gravity pulls inward, pressure pushes outward, energy flows from hotter regions to cooler ones. These principles apply whether we're studying a small flame on Earth or a star larger than the orbit of Jupiter. That continuity gives a sense of connection. The universe may be vast, but it is not alien in the sense of being governed by completely unfamiliar rules. It is understandable, at least in part, and that understanding grows steadily over time. There is also an emotional element to the way people respond to cosmic extremes. Looking at something vast or powerful can evoke a feeling sometimes described as awe. Awe is a mixture of admiration, curiosity, and a quiet awareness of one's own smallness. Psychologists have studied this feeling and found that it often has calming effects. Experiences of awe can reduce stress, increase patience, and encourage a sense of connection with the larger world. In that sense, thinking about giant stars and distant galaxies can be surprisingly soothing. It shifts attention away from immediate concerns and towards something larger and more enduring. Another interesting aspect of our fascination with extremes is that they give us boundaries to explore. When astronomers ask about the largest star, they are also asking about the limits of physics. How much mass can a star have? How large can it expand? What happens when those limits are reached? These questions are not only about stars, they are about understanding the laws of nature themselves. Every time a record is broken or a new extreme is discovered, it provides new information about what is possible in the universe. And sometimes, those discoveries lead to new theories or new technologies. For example, studying supernovae has helped astronomers understand the expansion of the universe. Observations of neutron stars and black holes have provided insights into gravity and the behavior of matter under extreme conditions. So the search for extremes is not just about curiosity, it is also a way of pushing the boundaries of knowledge. There is another layer to this fascination that is more personal. Human beings have a natural tendency to compare themselves with the world around them. We measure distances, heights, and times partly to understand our own place in the larger picture. When we learn about giant stars, it gives us a sense of scale that is difficult to obtain in any other way. The Sun, which seems enormous compared to Earth, becomes modest when compared to a red supergiant. The Earth, which feels vast when we travel across continents, becomes almost invisible when seen from the perspective of the galaxy. This shift in perspective can be humbling, but it can also be comforting. It reminds us that the universe is vast and that our own lives are small parts of a much larger story. At the same time, there is something remarkable about the fact that human beings, small as we are, can understand these immense objects. Through observation, mathematics, and careful reasoning, we have learned how stars are born, how they live, and how they die. That ability to understand, even partially, connects us to the universe in a meaningful way. Another reason people are drawn to cosmic extremes is that they inspire imagination. It is one thing to read that a star is large. It is another to imagine standing near it, seeing its vast surface, watching enormous currents of gas rise and fall. These imagined journeys help make abstract concepts more real. They allow us to explore places we can never physically visit, using only thought and description. In a quiet way, this kind of imagination can be restful. It encourages the mind to wander gently, to picture scenes that are distant and slow-moving, free from urgency or noise. There is also a sense of continuity in the story of the universe. Giant stars form, shine, and eventually explode, scattering the elements that will become part of new stars and planets. Over billions of years, this cycle has repeated countless times. Knowing this can create a feeling of connection across time. The atoms in our bodies were once part of stars that lived and died long before the Earth existed. In that sense, we are linked to the cosmos not just metaphorically, but physically. That idea often resonates deeply with people. It turns the study of astronomy from something distant into something personal. There's also the simple beauty of the night sky itself. Even without understanding the details of stellar evolution, people have always been drawn to the stars. The quiet, steady points of light, the slow movement of constellations through the seasons, and the sense of vast space above can create a feeling of calm that is difficult to find elsewhere. Modern astronomy adds new layers to that experience. When we look at a red star and know that it may be hundreds of times larger than the Sun, or that its light has travelled for centuries to reach us, the sky becomes richer with meaning. Another aspect of our fascination with extremes is that they help us think about time differently. Human life is measured in years and decades. Civilizations are measured in centuries. But stars evolve over millions or billions of years. Thinking about these timescales can change the way we perceive the present moment. It can make the passage of time feel slower, less hurried. That slower perspective is part of what makes science for sleep storytelling so effective. It encourages the mind to step away from the rapid pace of daily life and to settle into rhythms that unfold over much longer intervals. There is also a sense of mystery that remains, even as knowledge grows. Astronomers have learned a great deal about giant stars, but many questions remain. Exactly how large can a star become? How do the most massive stars form in detail? What processes occur in the final moments before a supernova? These unanswered questions keep the story open, inviting further exploration. And perhaps that is one of the deepest reasons humans are drawn to cosmic extremes. They remind us that the universe is larger than our current understanding, that there is always more to learn, more to discover, more to imagine. This sense of openness can be comforting rather than unsettling. It suggests that the story of the universe is ongoing, that curiosity and exploration will always have a place. As we come toward the end of this quiet journey, it helps to slow down for a moment and simply reflect on where we've been. We began by thinking about a single idea, the possibility of a star so large that it challenges our sense of scale. Along the way, we explored how stars are born, how they grow, how some of them expand into immense giants, and how their lives eventually come to an end in explosions that reshape entire regions of the galaxy. Yet beyond all the details and explanations, there is another layer to this story, one that is less about physics and more about perspective. Because when you think about stars that are hundreds or thousands of times larger than the Sun, something subtle begins to shift in the way you see the world. The mind stretches to accommodate distances and timescales far beyond ordinary experience. Problems that once felt enormous begin to feel smaller. Moments that once felt rushed begin to feel more spacious. It is not that everyday life becomes unimportant. Rather, it begins to feel part of a larger picture, one that is vast, patient, and quietly beautiful. Right now, wherever you're listening, you're sitting on a small planet orbiting a fairly ordinary star in a galaxy that contains hundreds of billions of stars, many of which are larger and more luminous than our Sun. Beyond our galaxy lie billions more galaxies, stretching outward in all directions, each one filled with its own stars, its own stories, its own slow unfolding of cosmic time. And yet here you are, able to think about all of it, to imagine it, to understand at least a small part of how it works. There is something remarkable in that simple fact. Human beings are small in physical scale, but the mind is capable of reaching outward across unimaginable distances. With a few quiet thoughts, you can picture a red supergiant glowing softly in the dark, or a supernova expanding into space, or a vast cloud of gas slowly forming new stars. That ability to imagine is part of what connects us to the universe. It allows us to participate in its story, even from a distance. If you were to step outside on a clear night and look up, most of the stars you would see would appear as tiny points of light. They would not reveal their true size or distance to your eyes. A giant star thousands of times larger than the Sun would look no different from a much smaller star, simply because it is so far away. This is one of the quiet lessons of astronomy. Appearance does not always reveal reality. The universe is deeper and more complex than it first appears, and understanding it requires patience and curiosity. There is also something peaceful about the steady nature of cosmic processes. Stars are born in clouds of gas, shine for millions or billions of years, and eventually fade or explode. Galaxies rotate slowly, their spiral arms turning over hundreds of millions of years. Even the expansion of the universe itself unfolds gradually, almost imperceptibly on human timescales. These rhythms are slow, steady, and unhurried. When you think about them, it can feel as though the pace of your own thoughts begins to slow as well, settling into a calmer, more relaxed pattern. Perhaps that is one of the reasons people have always found comfort in the night sky. Long before telescopes or scientific explanations, simply looking at the stars could create a sense of quiet connection, a feeling of being part of something vast and enduring. That feeling is still available today. The science adds detail and understanding, but the sense of calm remains much the same. Another thought worth lingering on is the idea that the elements in your body were once part of stars. The oxygen you breathe, the carbon in your cells, the iron in your blood, all were forged in stellar cores or in the explosions of dying stars long before the Earth existed. In a very real sense, you are connected to the life cycles of stars. The universe is not something separate from you. It is the environment from which you emerged. This idea does not need to feel grand or dramatic. It can simply be a quiet awareness, a reminder that the boundary between ourselves and the cosmos is not as sharp as it might seem. There is also a certain beauty in the impermanence of things. Giant stars, immense as they are, do not last forever. They shine brightly for a time, expand, change, and eventually end. Their material drifts into space, becoming part of new stars and planets. Nothing is wasted. The universe is constantly recycling matter and energy, reshaping itself in an ongoing cycle. When seen in this way, endings are not only endings, they are also beginnings, transitions in a process that continues on scales far larger than any individual star or planet. This perspective can be comforting in its own quiet way. It suggests that change is a natural part of the universe, not something to resist, but something to observe with patience and curiosity. As you think about the larger stars, the ones so vast that light takes hours to cross them, it may help to return to something simple and familiar, the feeling of breathing. Breathing is a slow, steady rhythm, a gentle cycle of inhaling and exhaling. Stars have their own rhythms as well, though on much longer timescales. They expand and contract, they lose mass in slow winds, they evolve gradually over millions of years. There is no hurry in these processes. Everything unfolds at the pace set by the laws of physics, a pace that is steady and reliable, and in that steadiness there is a kind of calm. Another quiet reflection arises when we consider how small our daily worries can seem in the context of cosmic time. A difficult day, a stressful moment, a lingering concern, these are real experiences and they matter. But they exist within a much larger framework, one that stretches across billions of years and countless stars. Remembering that larger framework does not erase difficulties, but it can soften them, placing them in perspective. It's a bit like standing on a shoreline and watching the ocean. The waves rise and fall, each one different, each one temporary, while the vast sea remains. In much the same way, individual moments in life rise and pass, while the larger universe continues its slow and steady unfolding. There is also a sense of companionship in knowing that countless other people, across different places and times, have looked up at the same sky and felt similar feelings of wonder. The stars have been a shared human experience for as long as people have existed. Even now, somewhere on Earth, someone is looking at the night sky, perhaps noticing a bright red star and wondering about its nature, just as we have done here together. That quiet continuity, the shared curiosity of generations, is part of what makes astronomy feel timeless. As this journey settles toward its end, it may be pleasant to imagine yourself lying under a clear sky, far from city lights. The air is cool and still. The stars are scattered across the darkness, steady and silent. Somewhere among them are giants, enormous stars glowing softly, their light travelling across space for thousands of years before reaching your eyes. You do not need to know their names or their exact distances to feel their presence. It is enough to know that they are there, part of the vast tapestry of the universe, And here, on this small world, in this quiet moment, you are part of that tapestry as well. There is nothing you need to do, nowhere you need to go. The universe is vast and patient, and there is time to simply rest, to breathe, and to let your thoughts drift gently, like clouds moving slowly across the sky. And as the mind grows quieter, it becomes easier to feel that sense of calm, the feeling of being small in a way that is not frightening but peaceful. The feeling of being present in a universe that is immense, beautiful, and endlessly unfolding, one quiet moment at a time.